Considerations for GNN projects. Welcome to Chapter 8, where we shift our focus from the theoretical underpinnings and scaling techniques of graph neural networks, GNNs, to the practical considerations of implementing them in real-world projects. Previous chapters, particularly graph representations, Chapter 2, introduced the fundamental ways to model data as graphs, and scaling training for large data, Chapter 7, equipped us with strategies to handle large-scale graph datasets. This chapter builds directly upon that knowledge, guiding you through the critical initial stages of a GNN project, data preparation and conversion. The journey from raw, often non-graph structured data to a format suitable for GNN training is a crucial and often complex part of the machine learning workflow. Unlike traditional machine learning models that typically operate on tabular data, GNNs require explicit graph structures, where entities, nodes, and their relationships, edges, are clearly defined. This section introduces the overall workflow, highlighting the importance of data, pre-processing, and graph construction, and sets the stage for the detailed discussions and hands-on examples that will follow throughout the chapter. The GNN project data workflow. A typical GNN project follows a structured workflow, beginning long before any model training occurs. Understanding these stages provides a mental model for how raw information is transformed into actionable insights through a GNN. Our journey begins with raw data, which often exists in non-graph formats such as relational databases, CSV files, text documents, or API feeds. This raw data contains the implicit relationships we aim to uncover or leverage. The next critical step is data cleaning and pre-processing. This phase involves standard data science practices, handling missing values, correcting inconsistencies, normalizing or scaling numerical features, transforming categorical data, filtering out irrelevant data. Crucially, in the context of GNNs, this stage also involves identifying which entities will become code snippet and which interactions will become code snippet. This is where the implicit relationships in your raw data start to become explicit. For instance, if you have a table of customer purchases, code snippet might be nodes, and code snippet or code snippet could become edges. Following cleaning, we move to feature engineering. Here, we derive meaningful attributes for our nodes and edges. Node features. These are properties of individual entities, like a person's age, income, or a product's category. Edge features. These describe the nature or strength of a relationship, such as the duration of a friendship, the transaction amount, or the type of interaction. These features are essential as GNNs propagate and aggregate information across the graph using these attributes. The core transformation for GNNs occurs during graph construction. This is where the pre-processed data, with its identified nodes and edges, is formally structured into a graph representation. Common intermediate representations include edge lists, a simple list of pairs where each pair code snippet denotes an edge between node code snippet and node code snippet. Adjacency lists, for each node, a list of its direct neighbors. Adjacency matrices, a matrix where rows and columns represent nodes, and a non-zero entry code snippet indicates an edge between node code snippet and node code snippet. Finally, this constructed graph is then converted into a specialized graph data structure for GNNs, typically provided by a graph neural network library, e.g., PyTorch Geometrics Code Snippet Object or DGL's code snippet. These structures are optimized for efficient GNN operations, allowing for the subsequent model training and evaluation phases, where the GNN learns from the graph structure and its features to perform tasks like node classification, link prediction, or graph classification. Converting non-graph data to graph structures. Many real-world data sets are not inherently represented as graphs. They often reside in tabular formats, relational databases, or unstructured text. However, many of the problems we want to solve with machine learning inherently involve relationships. GNNs excel precisely because they can directly model and learn from these relationships. The challenge, therefore, is to conceptualize and implement the transformation of this non-graph data into a GRA. PH format. This involves identifying the things, nodes, and the connections, edges, within your data. Consider a simple example, a tabular dataset representing people and their friendships. Code is not spoken. To get code, please see the link in description or bio. This CSV file is tabular, but it implicitly defines a graph where code snippet are nodes and code snippet indicates an edge, friendship, between them. To convert this into a graph, we first load it and identify the source and target nodes for our edges. Using the code snippet library, we can easily represent this data. Code is not spoken. To get code, please see the link in description or bio. This initial code snippet sets up our example. We're using code snippet to represent a simple table where each row signifies a connection between two individuals. Code snippet and code snippet will become the endpoints of our edges. This is a common way to represent relational data before explicit graph conversion. Now, let's explicitly extract the edge list from this data frame. An edge list is simply a collection of tuples, where each tuple code snippet indicates an edge from node code snippet to node code snippet. Code is not spoken. To get code, please see the link in description or bio. The code snippet function, combined with code snippet, efficiently transforms the two columns of our data frame into a list of tuples, directly forming our edge list. This is the first concrete step towards building a graph struct. Tour from tabular data. With the edge list in hand, we can now construct a graph using the code snippet library, a powerful tool for graph creation, manipulation, and analysis in Python. Code is not spoken. To get code, please see the link in description or bio. Here, code snippet initializes an empty, undirected graph. The code snippet method then populates this graph using our code snippet. This code snippet object code snippet now formally represents our friendship network, allowing us to perform graph-specific operations. And code snippet representation, though not explicitly coded here, would show for code snippet, for code snippet, and so on, listing direct neighbors for each node. The running example, a recruiting firm's social graph. Throughout this chapter, we will use a concrete running example. A recruiting firm that wants to leverage its network of candidates, recruiters, and companies to improve its operations. This scenario is ideal for GNNs because the core problem is inherently relational. Why GNNs are suitable for this problem? Interconnectedness. A recruiting firm's success heavily relies on the relationships between candidates and jobs, candidates and recruiters, recruiters and companies, and even candidates with other candidates, e.g., referrals. These are not isolated entities, but form a complex web. Relational inference. GNNs can learn from these explicit relationships to make predictions that go beyond individual attribute. For instance, a candidate's suitability for a job might depend not just on their resume, but also on who they know, who referred them, or the companies they've worked for and their connections to the recruiting firm. Pattern discovery. GNNs can identify complex patterns like which recruiter is best connected to companies hiring for a specific role, or which candidates are likely to be interested in a job based on their network's interests. Imagine the raw data for such a firm might include a table of code snippet with their skills, experience, and contact info, a table of code snippet with requirements, company, and salary, a table of code snippet with their specializations, a table of code snippet linking candidates to jobs, a table of code snippet linking candidates to other candidates, a table of code snippet linking candidates to recruiters for specific jobs. From this data, we could define our nodes and edges. Nodes, code snippet, code snippet, code snippet, code snippet, code snippet. Edges, code snippet, code snippet, code snippet, code snippet, code snippet, code snippet. This rich, interconnected structure is exactly what a GNN can process to perform tasks like link prediction, recommending suitable jobs to candidates or vice versa, or identifying potential referrals. Node classification, predicting if a candidate is high potential or if a job is hard to fill. Graph classification or subgraph classification, identifying successful hiring. patterns within specific company recruiter candidates subgraphs. Broadening the scope, other practical applications. Beyond a recruiting firm example, the process of converting non-graph data into graph structures is applicable across numerous domains. Financial transactions, raw data, bank transactions, sender, receiver, amount, timestamp. Nodes, accounts, individuals, businesses. Edges, code snippet from sender to receiver, code snippet. GNN task, fraud detection, identifying suspicious transaction patterns or money laundering rings. Document citation networks, raw data, research papers, articles, patents with their authors and reference lists. Nodes, documents, authors. Edges, code snippet, document A cites document B. Code snippet, author A co-authors with author B. GNN task, scientific paper recommendation, identifying influential papers or authors, topic modeling. Biological networks, raw data, experimental data on genes, proteins, drugs, and their interactions. Nodes, genes, proteins, molecules, drugs. Edges, code snippet, code snippet, code snippet. GNN task, drug discovery, predicting drug efficacy or side effects. Disease mechanism understanding. These examples underscore that wherever relationships and interactions are central to understanding a system, transforming data into a graph format for GNN analysis can yield powerful insights that might be missed by traditional models. Leveraging graph libraries. As we delve deeper into building and manipulating graph data, libraries like Code Snippet and Code Snippet become indispensable tools. Code Snippet provides a flexible and comprehensive API for general graph creation, manipulation, and analysis, making it excellent for initial graph construction and basic exploration. For GNN-specific operations, such as creating graph data objects optimized for deep learning frameworks, Code Snippet or Code Snippet are the go-to choices. These libraries bridge the gap between abstract graph concepts and the tensor operations required by GNN models, providing efficient data structures and ready-to-use graph neural network layers. We will explore their specific functionalities in subsequent sections. Data preparation and project planning. The success of any graph neural network, GNN, project hinges critically on the initial phases of understanding the problem, identifying relevant data, and meticulously preparing that data for graph representation. This section introduces a real-world business challenge from a recruiting firm, whole staffing, to illustrate these foundational steps. By framing this problem for a GNN solution, we'll explore how seemingly non-graph data can be conceptually transformed into a rich graph structure. Framing the problem, the whole staffing challenge. Whole staffing is a recruiting firm that connects job seekers with employers. Their core business relies on understanding candidate profiles, job requirements, and the intricate network of professional relationships, including referrals, past engagements, and shared connections. The challenge for whole staffing is to optimize candidate placement, identify high-potential talent, and leverage their network effectively. This involves answering questions like, which candidates are best suited for a specific job opening? Who are the most influential referrers in their network? Which candidates are likely to be interested in new opportunities based on their professional connections? Why a graph-based approach? At first glance, a recruiting database might appear as a collection of relational tables, candidates, jobs, applications, referrals. While traditional machine learning models can these tables, they often struggle to intrinsically capture and leverage the complex, multifaceted relationships between entities. This is where GNN excels. A GNN is uniquely suited for problems where relationships are paramount. In recruiting, the connection between a candidate and a referrer, a candidate and a job, or even two candidates who know each other, carries significant predictive power. These relationships are not just simple links, but can have associated attributes, e.g., strength of referral, date of interaction. Contextual information is vital. A candidate's suitability for a role isn't solely based on their resume, but also on who they know, what roles their connections hold, and their interaction history within a network. GNNs can aggregate information from a node's neighbors, providing a rich, contextualized representation. Network effects are present. The value of a candidate or a job opening can propagate through the network. A referral from a highly respected professional, for instance, might signal higher quality. GNNs inherently model these propagation effects. By modeling the recruiting ecosystem as a graph, whole staffing can uncover hidden patterns, identify influential nodes, and make more informed decisions that are impossible to discern from isolated data points. Conceptual data modeling for a GNN. The first step in building a GNN application is to translate the raw, often tabular or relational, business data into a graph structure. Involves identifying the nodes, entities, and edges, relationships within the data. Identifying core entities and relationships. For whole staffing, the primary entities and relationships can be conceptualized as follows. Potential nodes. Code snippet, an individual seeking employment. Code snippet, a specific open position at a company. Code snippet, an organization offering jobs. Code snippet, an employee at whole staffing. Code snippet, a specific ability or expertise, e.g., Python, project management. Potential edges, relationships. Code snippet, candidate to job. Code snippet, candidate to job after a successful application. Code snippet, candidate to company. Code snippet, candidate to skill. Code snippet, company to job. Code snippet, candidate, refer to candidate, referred. This is a crucial relationship for network analysis. Code snippet, job to recruiter. Code snippet, candidate to recruiter, representing engagement history. Hypothetical raw data and conceptual mapping. Let's consider simplified hypothetical raw data that whole staffing might possess in a relational database. 1. Candidate profiles, conceptual code snippet table. Code snippet code, snippet code, snippet code, snippet code, snippet code snippet. Code snippet Alice 8 software, ENG, NYC active. Code snippet Bob, 5 data, scientist, SF passive. Code snippet Charlie 12 engineering manager, NYC, open to new. 2. Referral history, conceptual code snippet table. Code snippet code, snippet code, snippet code, snippet code snippet. Code snippet code, snippet code, snippet strong, excellent problem solver. Code snippet code, snippet code, snippet medium, good networker, but needs more EXP. 3. Job openings, conceptual code snippet table. Code snippet code, snippet code, snippet code, snippet code snippet. Code snippet senior ML engineer code snippet Python. ML, AWS NYC. Code snippet data analyst code snippet SQL, Excel, Tableau SF. Mapping raw data to graph elements, code illustration. We'll use Python lists of dictionaries to represent our hypothetical raw data. Code is not spoken. To get code, please see the link in description or bio. This initial code snippet defines our raw, tabular data. Each dictionary represents a row in a conceptual database table. We'll now see how to transform these into graph nodes and edges. Extracting nodes and node features. Each row in the code snippet and code snippet tables can be directly mapped to a node in our graph. The columns of these tables become node features. Code is not spoken. To get code, please see the link in description or bio. In this step, we iterate through our raw data to create distinct nodes. 4 code snippet nodes. Code snippet serves as the unique identifier, while code snippet, code snippet, code snippet, code snippet, and code snippet become descriptive features associated with that node. Similarly, for code snippet nodes, code snippet is the identifier, and code snippet, code snippet, code snippet, and code snippet are its features. These features are crucial for GNNs, as they provide the initial information that the network propagates and transforms. Extracting edges and edge attributes. Relationships between entities form the edges of our graph. The code snippet directly provides information for code snippet edges. Other relationships, like code snippet or code snippet, will be derived from other conceptual tables, not shown here for brevity, but following a similar logic. Code is not spoken. To get code, please see the link in description or bio. Here, each entry in code snippet becomes a code snippet edge. The code snippet is the source node, and code snippet is the target node. Importantly, code snippet and code snippet are extracted as edge attributes. These attributes provide additional context to the relationship itself, allowing the GNN to understand not just that a referral exists, but also when it happened and how strong it was. This enriches the graph structure beyond simple binary connections. Challenges and considerations in data conversion. C. Converting raw data to a graph format is not always straightforward. Several practical challenges and ambiguities can arise. 1. Defining edge weights from engagement history. If code snippet, e.g., number of interactions, duration of calls, is available, how do you quantify the strength of encode snippet edge? This might involve feature engineering, e.g., recency weighting, frequency counts, to derive meaningful numerical edge weights. 2. Handling missing data. What happens if a code snippet is missing? Should the edge be excluded, assigned a default value, or imputed? The choice depends on the domain and the downstream GNN model's robustness to missing features. 3. Ambiguous relationships. Sometimes, a single raw data entry might imply multiple relationships, or the relationship type itself might be ambiguous. Clear domain understanding is essential to define precise edge semantics. 4. Graph sparsity versus density. Not all entities might have direct connections. A very sparse graph, few edges, can limit the GNN's ability to propagate information, while an overly dense graph can introduce noise. Strategies like adding virtual edges, e.g., connecting candidates with similar skills, might be considered, but carefully. 5. Dynamic graphs. Real-world data, like recruiting interactions, is often time-evolving. New candidates join, referrals are made, jobs open and close. Deciding how to represent these temporal dynamics, e.g., using time-stamped edges or snapshots over time, is a critical design choice. What questions can a GNN answer for whole staffing? Once the data is transformed into a graph, GNNs can be applied to solve various predictive and analytical tasks. Candidate recommendation, node classification/link prediction given a job opening. Which candidates in the network are most suitable? This could involve classifying candidates based on their likelihood to be a good fit or predicting a code snippet link between a candidate and a job. Talent pool expansion, link prediction, identifying potential candidates who are not yet in the database, but are connected to high-quality existing candidates. This involves predicting new code snippet links. Influencer identification, node centrality/importance, pinpointing which recruiters or candidates are central to the network and have a most impact on successful placements or referrals. This can inform resource allocation and strategy. Job skill matching, graph matching/similarity, finding jobs that closely match a candidate's skill set and experience, considering not just explicit skills, but also implied skills from their network. Churn prediction, node classification, identifying candidates who might become inactive or disengaged based on their network activity or lack thereof. Broader real-world analogies. The principles of problem framing and data preparation for whole staffing are broadly applicable across many industries. E-commerce, building customer product interaction graph. S to recommend products, identify fraudulent transactions, or analyze customer segments. Nodes could be customers, products, categories. Edges could be purchased, viewed, reviewed. Healthcare, constructing patient disease drug graphs to predict drug interactions, identify disease outbreaks, or personalized treatment plans. Nodes could be patients, diseases, symptoms, drugs. Edges could be diagnosed with treated by causes. Financial services, modeling transaction networks to detect money laundering, predict stock market trends, or assess credit risk. Nodes could be accounts, transactions, entities. Edges could be transfers to own shares in. Supply chain management. Analyzing supplier manufacturer distributor networks to optimize logistics, predict disruptions, or improve resilience. Nodes could be companies, warehouses, products. Edges could be supplies, ships via. In each of these domains, the ability to represent complex relationships as a graph and leverage GNNs to learn from these structures unlocks powerful insights and predictive capabilities that are difficult to achieve with traditional methods. Data preparation and project planning. The initial phase of any graph neural network, GNN, project is crucial, laying the groundwork for successful model development and deployment. This involves clearly defining the problem, understanding the available data, and conceptualizing how that data can be structured as a graph. Defining the problem for GNNs. A well-defined problem statement is the cornerstone of any machine learning initiative. For GNNs, this involves translating business questions into specific graph-based tasks. Consider a hypothetical recruiting firm, whole staffing, which aims to optimize its talent placement process. Translating business needs to GNN tasks. Whole staffing faces several challenges. 1. Missing data in candidate profiles. Recruiters often have incomplete information about candidate skills, past projects, or team preferences. 2. Identifying compatible individuals and teams. It's difficult to predict which candidates will work well together on a project or which candidates are a good fit for a specific team's dynamic. 3. Leveraging referral networks. The firm has a rich history of referrals, but extracting actionable insights from this network is challenging. These business questions, while seemingly distinct, can be framed as GNN problems. Missing data in profiles, e.g., a candidate's specific skill set. This can be approached as a node feature prediction or node classification task. If we model candidates as nodes and their attributes. As node features, a GNN can learn to infer missing features based on a candidate's connections, e.g., referrals, shared past projects, and the features of their connected neighbors. It can also be framed as a link prediction task if missing information implies a missing connection, e.g., predicting if a candidate should have a certain skill based on who they know. Identifying compatible individuals/teams. This naturally lends itself to link prediction, predicting if a new connection or compatibility link should exist between two individuals or an individual and a team. Community detection, grouping individuals who are likely to work well together into communities or node similarity. Finding individuals with similar network positions or attributes indicative of compatibility. Leveraging referral networks. This is a classic social network analysis problem. GNNs can be used to understand influence, identify key connectors, high-degree nodes, or predict future referral links. The process begins by converting these abstract business challenges into concrete, graph-centric machine learning tasks. The GNN project lifecycle. Initial stages. The early stages of a GNN project involve distinct, yet interconnected, steps. Project definition. The what. This phase focuses on precisely articulating the problem to be solved. What are the core business questions? What are the desired outcomes or metrics of success, e.g., improved placement rate, reduced time to hire? Can the problem truly be modeled as a graph? And if so, what are the primary entities and relationships? Requirements analysis. The how. Conceptual. Once the problem is defined, this phase explores the conceptual approach. What GNN task type, e.g., node classification, link prediction, aligns best with the problem? What kind of data is available, and what form does it take? What are the initial assumptions about the graph structure, e.g., directed versus undirected, weighted versus unweighted? Initial data modeling. The how. Practical. This phase translates the conceptual understanding into a concrete graph representation. How will raw data be transformed into nodes and edges? What features will be extracted for nodes and edges? How will simplifying assumptions be applied? And what are their implications? Conceptualizing data as a graph. The core of data preparation for GNNs is transforming raw, often tabular, data into a graph structure. This involves identifying what constitutes a node and what constitutes an edge within your problem domain, identifying entities and relationships. For whole staffing, let's consider the referral network. Nodes. The most obvious nodes are the code snippet or code snippet within the firm's network. Edges. A code snippet from one employee to another naturally forms an edge. Consider a simplified dataset of referrals. Referred. Alice Bob, Bob Carol, Alice David, CA, role Alice, David Eve. We can represent this in Python using a list of tuples to define the edges. Code is not spoken. To get code, please see the link in description or bio. This initial step extracts all unique individuals involved in the referrals, which will form the nodes of our graph. Graph simplifications, undirected and unweighted graphs. For our initial modeling of the referral network, we might choose to represent it as an undirected and unweighted graph. Undirected. An edge between Alice and Bob means they have a mutual connection, regardless of who referred whom. If Alice refers Bob and Bob refers Alice, it's considered a single shared connection. Even if only Alice refers Bob, for simplicity, we might treat it as a symmetric relationship in an undirected graph. Unweighted. The edges simply indicate the existence of a referral relationship, not its strength or frequency. Let's see how this translates to graph creation using the code snippet library. Code is not spoken. To get code, please see the link in description or bio. The output shows the number of nodes, 5, Alice, Bob, Carol, David, Eve, and edges 4, Alice, Bob, Alice, Carol, Alice, David, David, Eve. Notice that code snippet and code snippet become code snippet and code snippet in the undirected graph. The edge code snippet is automatically handled as the same edge as code snippet by code snippet for an undirected graph. Rationale and implications of simplification. Rationale FO are undirected and unweighted. Simplicity for initial exploration. For first pass, focusing on the sheer existence of a connection simplifies the problem. It allows for quick prototyping and understanding of a network's basic topology without getting bogged down in intricate details. Computational efficiency. Simpler graphs often require less computational power and memory, which is beneficial during the early stages of model development. Problem focus. If the primary goal is simply to identify who knows whom or who is connected to whom for initial compatibility assessment, the direction or strength of the referral might be secondary. Implications and trade-offs. Loss of information. By making a graph undirected and unweighted, we lose valuable information. Directionality. We can no longer distinguish between Alice referred Bob and Bob referred Alice. This might be crucial if, for example, referrals from senior staff carry more weight or imply a different kind of relationship. Weight/strength. We lose insight into the strength of the relationship. Was a strong, direct referral or a casual mention? Was there only one referral or many? Impact on GNN tasks. For link prediction, an undirected graph might suffice if we're simply predicting any future connection. However, if we need to predict who will refer whom, directionality becomes essential. For node feature prediction or community detection, the lack of weight might mean that all connections are treated equally, potentially overlooking strong ties that are more indicative of shared attributes or group membership. It's crucial to understand these trade-offs. While simplification aids initial progress, a more complex, directed, weighted graph might be necessary for achieving higher accuracy or answering more nuanced business questions in later stages. Addressing missing data with GNNs. The problem of missing data in candidate profiles is a common challenge. GNNs offer powerful mechanisms to impute or infer missing information by leveraging the graph structure. Node feature imputation. Imagine a candidate profile where some skills are missing. If this candidate is connected to several other candidates who possess specific skills, a GNN can propagate information across the graph to infer the likely missing skills. Consider a scenario where code snippet has a missing skill. Code is not spoken. To get code, please see the link in description or bio. Here, code snippet for code snippet is unknown. If code snippet is strongly connected to code snippet and code snippet, who both have code snippet, a GNN could learn to predict that code snippet likely also possesses code snippet. The GNN effectively fills in the blanks by considering local neighborhood information and global graph patterns. This is often achieved through node classification, predicting a categorical skill, or node regression, predicting a continuous attribute. Link prediction for missing connections. Sometimes missing data isn't about an attribute of a node, but about a missing relationship. For instance, two employees might implicitly work well together based on their shared network, but no explicit compatibility link exists. A GNN can predict these latent or missing connections. For example, if code snippet and code snippet have never worked together directly, but they both have strong connections to code snippet, a GNN might predict a high probability of a future direct collaboration or compatibility link between code snippet and code snippet. This is a direct application of link prediction, where the GNN learns patterns from existing links to infer non-existent ones. Broader applications of graph structures. The principles applied to whole staffing problems extend across numerous industries and domains. Understanding these broader applications helps in identifying potential GNN use cases in various real-world scenarios. Product recommendation systems. Similar to identifying compatible individuals, GNNs can recommend products, nodes to users, nodes, by modeling user-product interactions as a bipartite graph, or by finding similar users/products within a complex network. Fraud detection. Financial transactions, accounts, and individuals can be modeled as a graph. Fraudulent activities often manifest as unusual patterns or dense subgraphs, which GNNs are adept at identifying. Drug discovery and material science. Molecules and compounds are inherently graph-s. Structured. GNNs can predict molecular properties, identify potential drug candidates, or simulate material behaviors by learning from their atomic structures and bonds. Cybersecurity. Network traffic, user access patterns, and device connections can form a graph. GNNs can detect anomalies, identify malicious actors, or predict potential attack paths. Supply chain optimization. Suppliers, manufacturers, distributors, and retailers form complex networks. GNNs can optimize logistics, predict disruptions, or identify vulnerabilities within the supply chain. By understanding how to frame business problems as graph problems and apply initial data modeling principles, you unlock a vast array of possibilities for GNNs to solve complex, interconnected challenges. Project objectives and scope. Before embarking on any graph neural network, GNN, project, a thorough understanding of its objectives, requirements, and scope is paramount. This foundational planning phase prevents common pitfalls such as scope creep, misaligned expectations, and the development of solutions that don't meet real-world needs. For a GNN project, this involves not only technical considerations, but also crucial non-technical factors like data privacy and model explainability. Defining project objectives. The very first step is to clearly articulate what the GNN project aims to achieve. Vague objectives lead to unfocused efforts and make it impossible to measure success. A business problem, such as optimizing staff allocation, needs to be translated into a precise, actionable GNN objective. For instance, in our whole staffing running example, a broad business goal like improve operational efficiency can be refined into a GNN-specific objective. Develop a GNN model to predict optimal staff assignments for upcoming shifts, minimizing understaffing and overtime by identifying skill gaps and social connections among employees within a 24-hour prediction window, achieving 90% accuracy in shift coverage predictions. This objective adheres to the SMART criteria. Specific, predicts optimal staff assignments, minimizes understaffing/overtime, identifies skill gaps/social connections. Measurable, 90% accuracy in shift coverage predictions, 24-hour prediction win. Doubt, achievable, given available data and resources. Relevant, directly addresses the business need for operational efficiency. Time-bound, implied by upcoming shifts and 24-hour prediction window, typically tied to a project timeline. Common pitfall, starting development without clearly defined, measurable objectives. This often results in solutions that are technically impressive but fail to address the core business problem, or projects that endlessly pivot without reaching a deployable state. Identifying project requirements. Once objectives are clear, the next step is to define the specific conditions the GNN solution must satisfy. These requirements typically fall into two categories. 1. Functional requirements, what the system must do. For whole staffing, this includes predicting missing shifts, suggesting alternative staff, identifying overstaffed areas, or recommending cross-training opportunities. 2. Non-functional requirements, NFRs, how well the system performs or operates. These are critical for GNN projects as they heavily influence architectural decisions, data strategies, and model choices. Neglecting NFRs can lead to solutions that are technically sound, but practically unusable or legally non-compliant. Let's delve into key non-functional requirements specific to GNN projects. Data size and velocity. This requirement addresses the volume, variety, and rate of change of your graph data. Understanding this is crucial for selecting appropriate to goals and infrastructure. Explanation. How many nodes and edges are in your graph? What is the dimensionality of node and edge features? How frequently does the graph structure or its attributes change? A static graph of 100 nodes has vastly different implications than a dynamic graph with billions of nodes and millions of updates per second. Impact on GNN design. Infrastructure. Small graphs, thousands of nodes, might be processed on a single machine using libraries like PyTorch Geometric, Code Snippet, or Deep Graph Library, Code Snippet. Large graphs, millions to billions of nodes, necessitate distributed computing frameworks, e.g., Spark GraphX, DGL/PYG, with distributed training capabilities, or specialized graph databases. Storage. The choice between relational databases for tabular data that can be joined to form a graph, dedicated graph databases, e.g., Neo4j, ArangoDB, optimized for graph traversal, or distributed file systems, e.g., HDFS, depends on scale and query patterns. GNN architecture. For very large graphs that cannot fit into memory, GNNs must employ sampling techniques, e.g., node-wise sampling, neighbor sampling, subref sampling, during training to process many batches of nodes and their local neighborhoods, rather than the entire graph. This impacts how messages propagate and aggregate. Quantification. Volume. The graph will have approximately 1 million nodes and 10 million edges. Feature complexity. Each node will have 50 features, edges W. It'll have 5 features. Velocity. The graph structure updates with 10,000 new nodes/edges per hour. Whole staffing example. In whole staffing, quantifying the number of employees, nodes, their relationships, edges, e.g., works with has same skill, and the frequency of schedule changes, updates to edge attributes or new edges representing shifts, directly influences the choice of graph representation and processing pipeline. If schedules change hourly, a dynamic graph approach might be needed. Inference speed and latency. This requirement defines how quickly the GNN must produce a prediction or recommendation once new input is provided. Explanation. Is the GNN providing real-time recommendations, e.g., suggesting a staff member instantly when shift opens up, or generating daily reports, e.g., optimizing the next week's schedule overnight? Impact on GNN design. Model choice. Simpler GNN architectures, e.g., a few layers of graph convolutional networks, GCN, or GraphSage, generally offer lower inference latency. Deeper, more complex models, or those requiring extensive neighborhood aggregation, might be slower. The trade-off here is often between accuracy and speed. Deployment strategy. Real-time requires an API endpoint, potentially with model-serving frameworks, e.g., TensorFlow serving, torch serve, and efficient graph query capabilities. Batch can be run as a scheduled job, allowing for more computationally intensive models or larger graph traversals. Hardware. For very low latency requirements, specialized hardware like GPUs or TPUs might be necessary, even for inference. Edge deployment, running the model on local devices, might require highly optimized small models. Optimization. Techniques like model pruning, removing unnecessary connections, quantization, reducing numerical precision, and graph partitioning, dividing the graph for parallel processing, can significantly improve inference speed. Quantification. The model must provide a prediction within 500 milliseconds for 95% of requests, or the daily batch job must complete within 2 hours. Whole staffing example. If a manager needs to fill an urgent shift due to an unexpected absence, the system needs to suggest candidates almost instantaneously. This demands low latency. If the system is for weekly schedule optimization, an overnight batch process is acceptable. Data privacy and anonymization. This is a critical non-technical requirement, especially when dealing with sensitive personal data, as is often the case in staffing or social network applications. Explanation. Ensuring that personal or sensitive information within the graph data is protected and not inadvertently exposed or used inappropriately. This is driven by ethical considerations and legal regulations. Regulatory context. Different regions have distinct data privacy laws. The General Data Protection Regulation, GDPR, in Europe, the California Consumer Privacy Act, CCPA, in the U.S., and IPAA for health information are prominent examples. These regulations dictate how data is collected, stored, processed, and shared, often requiring explicit consent, data minimization, and the right to be forgotten. Neglecting these can lead to severe legal penalties and reputational damage. Techniques and impact on GNN design. Anonymization/pseudonymization. Removing direct identifiers, e.g., names, IDs, or replacing them with pseudonyms. For graph data, this might involve techniques like k-anonymity, ensuring each individual is indistinguishable from at least k, one other individuals, or differential privacy. Data generalization/aggregation, representing data at a higher level of abstraction, e.g., age ranges instead of exact age, department instead of specific employee. Synthetic data generation, creating artificial datasets that mimic the statistical properties of the real data but contain no actual private information. Differential privacy, DP, adding carefully calibrated noise to data or model gradients during training to guarantee privacy. This can impact model accuracy and training complexity. Federated learning, training GNNs on decentralized datasets, e.g., on individual devices or separate organizational silos, without ever consolidating the raw data. Only model updates or gradients are shared. This requires specialized GNN architectures that support distributed training. Trade-offs. Stricter privacy measures often come at the cost of data utility potential, while leading to less accurate or less comprehensive models. The balance must be carefully managed. Whole staffing example. Employee names, salaries, performance reviews, and even their relationships, e.g., friend of X, can be highly sensitive. The GNN should operate on anonymized employee IDs, aggregated skill sets, and generalized shift patterns. How do you represent who works well with whom without explicitly linking to individuals? Perhaps through aggregated shift overlap data or shared project histories. Model explainability. This requirement refers to the ability to understand why a GNN made a particular prediction or recommendation. Explanation. In many real-world applications, a black box model is insufficient. Stakeholders, managers, employees, regulators need to understand the rationale behind a decision. For instance, why was person A recommended for a shift over person B? Why did the model predict a staffing shortage in a particular department? Why it's important. Trust and adoption. Users are more likely to trust and adopt a system if they understand its reasoning. Debugging. Explainability helps identify model biases, errors, or unexpected behaviors. Compliance. In regulated industries, e.g., finance, healthcare, explainable AI, XAI, is increasingly becoming a regulatory requirement. Business insights. Explanations can reveal new insights about the underlying graph structure or data relationships. Impact on GNN design. Model choice. Simpler GNN MO. DELs, e.g., shallow GCNs, are often more inherently interpretable than very deep or complex architectures. Post hoc explainers. For complex GNNs, post hoc explanation techniques are used. These include GNN-specific explainers, tools like Code Snippet or Code Snippet, from PyTorch Geometric or DGL, aim to identify the most influential nodes, edges, or features in the input graph that contribute to a specific prediction. General ML explainers, adapting techniques like LIME, local interpretable model-agnostic explanations, or SHAP, Shapley additive explanations, to graph data. Feature importance, understanding which node/edge features are most salient for a given task. Trade-offs, there's often a trade-off between model complexity/accuracy and explainability. Highly accurate. Complex models tend to be less inherently explainable. Implementing explainability techniques can also add computational overhead to inference. Whole staffing example. If the GNN recommends a specific employee for a critical shift, an explanation could highlight factors like employee X was chosen because they have the required skills, skill A, skill B. They have positive past coworker ratings with the existing team members for that shift, and they are available during those hours. Conversely, if a staffing gap is predicted, the explanation could point to lack of employees with skill C available on that day, compounded by 2 key employees being on vacation. Project scoping and iteration. DEFI. Ning the project scope involves setting clear boundaries for what the GNN project will and will not deliver. This manages expectations and helps allocate resources effectively. In scope versus out of scope. Clearly delineate the functionalities and features that are part of the current project phase. For whole staffing, an initial scope might be predicting understaffing for core shifts in department, while optimizing employee satisfaction based on social network analysis might be out of scope for the first iteration. Minimum viable product, MVP, for complex GNN projects, consider an MVP approach. Start with a simplified version that delivers core value, gather feedback, and then iterate. This allows for early validation and reduces risk. Iterative nature of planning. Project planning is rarely a one-time event. As the project progresses, new data insights might emerge, model performance might reveal unexpected challenges, or business needs might evolve. Therefore, requirements and scope should be revisited and refined iteratively. This agile approach allows for flexibility and adaptation. Problem decomposition. Large problems can be broken down into smaller, manageable subproblems. For whole staffing, this could mean separate GNN models for skill prediction, shift compatibility, and demand forecasting, which are then integrated. Each subproblem can have its own mini-scope and objectives. By meticulously defining objectives, identifying comprehensive requirements, both functional and non-functional, and carefully scoping the project, you lay a robust foundation for a successful GNN implementation, ensuring that the final solution is not only technically sound, but also practically valuable, compliant, and trustworthy. Designing graph models is a foundational, yet often challenging, step in any graph neural network, GNN project. Unlike traditional tabular data, where rows and columns have clear, predefined meanings, graph representation inherently carries a degree of ambiguity. The same underlying real-world entities and relationships can often be modeled in multiple valid graph structures, each with different implications for downstream GNN tasks. This section outlines a systematic process to navigate this ambiguity and create robust graph data models. The process for designing effective graph models can be broken down into 4 iterative phases: understand, design, test, and refactor. 1. Understand the data and use case. Before drawing any nodes or edges, the most critical step is to deeply understand both the raw data sources and the specific problem you're trying to solve with a GNN. This understanding informs every subsequent modeling decision. Understanding the raw data. Begin by thoroughly inspecting your raw, non-graph data. This typically comes in tabular formats, e.g., CSV files, relational database tables, but could also be semi-structured, JSON, XML, or unstructured, text, images. Consider the following questions to guide your data understanding. What are the primary entities or objects? E.g., in whole staffing, candidates, jobs, teams, skills, referrals. What attributes describe these entities? E.g., for a candidate, name, experience, education, current role. How are these entities related to each other? E.g., a candidate refers another candidate. A candidate applies for a job. A candidate possesses a skill. What is the cardinality of these relationships? E.g., one-to-one, one-to-many, many-to-many. What is the typical volume and velocity of this data? E.g., thousands of candidates, millions of referrals. What is the quality of the data? E.g., missing values, inconsistencies, data types. Let's consider a simplified version of the whole staffing data, focusing on candidates and their referrals, which might initially reside in a tabular format. Code is not spoken. To get code, please see the link in description or bio. Code is not spoken. To get code, please see the link in description or bio. This initial tabular data provides the raw ingredients for our graph. Understanding the use case and GNN task. The specific GNN task you intend to perform is paramount. This objective will dictate which entities become nodes, which relationships become edges, and what properties are important. What business problem are you trying to solve? E.g., identify the most influential candidates for recruiting, predict which candidates are most likely to accept a job offer, find compatible teams based on candidate skills and referrals. What GNN task maps to this problem? Node classification, predicting a property of a node, e.g., a candidate's potential success, their job role. Link prediction, predicting the existence or type of a relationship between nodes, e.g., predicting a future referral, team compatibility. Graph classification, predicting a property of an entire graph, less common for whole staffing but relevant for molecular graphs, etc. Node regression, link regression, etc. For the whole staffing example, if our goal is to predict team compatibility, a link prediction task between candidates, or identify influential candidates, a node classification/ranking task. Our graph model will be structured differently than if we were trying to predict candidate churn, another node classification task. 2. Design the graph model. With a clear understanding of the data and the use case, you can begin to design your graph model. This phase involves defining the conceptual model, formalizing it into a schema, and illustrating it with an instance model. Data model, schema, and instance model. These three terms are often used interchangeably, but they represent distinct levels of abstraction in graph design. Data model, conceptual model. This is the high-level, abstract representation of your graph. It defines the types of entities, potential node types, and relationships, potential edge types, and their key properties, often sketched on a whiteboard. It answers, what things do I care about, and how are they connected? Schema, logical model. This is the formal, structured definition of your graph model. It specifies the exact node labels, edge labels, and the properties with their data types that each node and edge type can have. It defines the rules for your graph. A schema acts as a blueprint, ensuring consistency. Instance model, physical model. This is the actual graph data that conforms to your schema, populated with real-world instances of nodes and edges from your raw data. It's the concrete realization of your design. Step-by-step graph modeling for whole staffing. Let's walk through designing a graph model for our simplified whole staffing data, illustrating the ambiguity and implications. Initial tabular data, recap. Code snippet, 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 code snippet. Goal, understand candidate relationships, potentially for link prediction, e.g., predicting future referrals or team compatibility, or node classification, e.g., predicting candidate influence. Option 1. Candidates as nodes, referrals as edges. This is a common and intuitive approach. Nodes, code snippet, identified by code snippet. Edges, code snippet, connecting a code snippet to a code snippet. Node properties, code snippet, code snippet, code snippet. Edge properties, code snippet, code snippet. Conceptual data model, mental sketch. Code is not spoken. To get code, please see the link in description or bio. Formal graph schema, Python dictionary representation. We could define a simple Python dictionary to represent our graph schema. In real-world graph databases, TS would be a formal schema definition language, e.g., CipherDDL for Neo, 4J, GQL. Code is not spoken. To get code, please see the link in description or bio. Code is not spoken. To get code, please see the link in description or bio. Instance model, creating the graph with NetworkX. Now, let's create a graph instance from our tabular data using this schema. We'll use the code snippet library, a popular choice for graph creation and analysis in Python. Code is not spoken. To get code, please see the link in description or bio. Code is not spoken. To get code, please see the link in description or bio. This graph represents candidates as nodes and referrals as direct connections between them. This model is excellent for tasks like link prediction, predicting if Alice will refer Charlie, if no edge exists. Node classification, predicting if a candidate is influential based on their position in the referral network. Community detection, finding clusters of candidates who refer each other frequently. Option 2. Candidates and referrals as nodes, bipartite-like or hypergraph-like. What if the code snippet itself holds important information, or we want to model more complex interactions involving the referral event itself? We could elevate the code snippet from an edge to its own node. Nodes, code snippet from code snippet, and code snippet from code snippet. Edges, code snippet connecting a code snippet to the code snippet. Code snippet connecting a code snip. Pet to the code snippet. Node properties, code snippet, code snippet, code snippet, code snippet. Code snippet, code snippet, code snippet. Edge properties, none needed in this specific model, as all properties are on the code snippet node. Conceptual data model, mental sketch. Code is not spoken. To get code, please see the link in description or bio. Formal graph schema, Python dictionary representation. Code is not spoken. To get code, please see the link in description or bio. Code is not spoken. To get code, please see the link in description or bio. Instance model, creating the graph with NetworkX. Code is not spoken. To get code, please see the link in description or bio. Code is not spoken. To get code, please see the link in description or bio. Notice how code snippet has more nodes. 5 candidates plus 3 referral events equals 8 nodes. And more edges. 3 referral events, 2 edges, each equals 6 edges, compared to code snippet. Implications of different models. The choice between option 1 and option 2, or other variations, depends heavily on the GNN task. Option 1, referrals as edges. Pros, simpler graph structure, fewer nodes, potentially faster GNN training for simple tasks. Directly models the who referred whom relationship. Ideal for classic link prediction or node classification based on direct network centrality. Cons, if referral properties, code snippet, are crucial for complex interactions, they're only edge attributes. Some GNNs might not handle edge attributes as richly as node attributes. If a referral event itself has multiple participants or complex internal structure, this model oversimplifies it. GNN impact. More suitable for GNNs that primarily aggregate features from direct neighbors and edge types. Option 2, referrals as nodes. Pros, allows code snippet to have its own rich set of properties and participate in more complex relationships, e.g., if a referral is also linked to a code snippet. Facilitates modeling of hypergraphs, where an edge connects more than two nodes, here represented by a central node. Enables node classification on code snippet nodes, e.g., predicting referral success. Cons: more complex graph structure, more nodes and edges, potentially slower GNN training. Requires GNN architectures that can handle heterogeneous graphs, multiple node and edge types. GNN impact: better for heterogeneous GNNs, e.g., GraphSage with type-specific aggregations, or when the event itself is a primary entity of interest for prediction. It allows for richer feature engineering by using features of the code snippet node in convolutions. This demonstrates the inherent ambiguity, two equally valid ways to represent the same underlying data, but with different structures and implications for GNNs. The best choice is always context-dependent. Common pitfalls and best practices in design. What should be a node, an edge, or a property? Node: a distinct entity that has an identity in propert, IES, and is the subject or object of relationships. If you need to attach attributes to it, or if it could be a source/destination of multiple relationship types, it's likely a node. Edge represents a relationship between two nodes. If the relationship itself has properties that are critical for your task, e.g., code snippet, consider if those properties are simple attributes of the relationship, or if the relationship itself is complex enough to warrant being its own node, as shown in option 2. Property: an attribute describing a node or an edge. Properties are typically scalar values, numbers, strings, booleans. If an attribute needs to be connected to other entities or can itself have attributes, it's probably a node. Overnormalization versus undernormalization. Don't normalize your graph too much, e.g., making every single attribute its own node, or too little, e.g., cramming complex relationships into simple edge properties. Find a balance that serves your GNN task. Directionality. Always consider if relationships are directed, e.g., it refers B, but B does not necessarily refer A, or undirected. Self-loops and parallel edges. Decide if your model allows a node to connect to itself, self-loop, or if multiple edges of the same type can exist between the same two nodes, parallel edges. Domain expertise. Leverage domain experts. They understand the nuances of the data and relationships that might not be obvious from raw data. 3. Test your model. Once you have a designed graph model and an instance of it, it's crucial to test its validity and suitability. This isn't about testing GNN performance yet, but about ensuring the graph correctly represents the data and supports your intended analysis. Testing your graph model involves schema conformance. Does your instance graph actually adhere to the defined schema? Are all nodes and edges of the correct types, and do they have the expected properties? Data integrity. Are there any missing nodes or edges that should be present? Are there duplicate entries? Connectivity and structure. Does the graph exhibit the expected connectivity patterns? Are there isolated nodes? Are there dense clusters where expected? Querying for insights. Can you easily retrieve the information required for your GNN task? For example, can you find all candidates referred by Alice? Can you find all referrals with high strength? Example validation checks using NetworkX. Code is not spoken. To get code, please see the link in description or bio. Code is not spoken. To get code, please see the link in description or bio. These checks help confirm that the transformation from tabular data to graph data was successful and that the graph structure aligns with the conceptual design. 4. Refine and iterate. Graph modeling is rarely a one-shot process. After designing and testing, you'll likely find areas for refinement. Feedback from testing. Did the graph represent the data as expected? Were there unexpected disconnections or missing relationships? GNN performance. Once you start training GNNs, you might discover that certain modeling choices, e.g., what constitutes a node versus an edge property, lead to better or worse performance. This often prompts a return to the design phase. New requirements. As your project evolves, new business questions or data sources might emerge, requiring adjustments to your graph model. This iterative process of understanding, designing, testing, and refining ensures that your graph model is robust, accurate, and optimized for your specific GNN application. The quality of your graph model directly impacts the success of your GNN project. Get familiar with the domain and use case. Before embarking on any graph neural network, GNN, project, the most crucial initial step is not to dive into intricate model architectures or coding. Instead, it is to thoroughly understand the problem domain and the raw data at hand. This foundational phase ensures that the resulting graph model is not only technically sound, but also relevant, accurate, and truly addresses the business challenge. Without this deep understanding, even the most sophisticated GNN might yield irrelevant or misleading results. Systematically acquiring domain knowledge. Acquiring domain knowledge is an iterative process that involves more than just looking at data. It requires active engagement with stakeholders and existing resources. Interviewing stakeholders. Engage directly with the people who understand the business problem best. These could be business analysts, product managers, sales teams, or domain experts. Ask open-ended questions about their current processes, pain points, desired outcomes, and what success looks like. For example, in a recruitment scenario, questions might include, what are the common challenges in finding qualified candidates? How are referrals currently handled? What makes a referral good or bad? What metrics are used to measure recruitment success? Reviewing existing documentation and reports. Businesses often have internal reports, standard operating procedures, data dictionaries, and past analyses. These resources can provide valuable context, definitions, and insights into historical trends and business rules. Competitive analysis and industry best practices. Understanding how similar problems are addressed in your industry or by competitors can spark ideas and highlight common data patterns or relational structures. Shadowing domain experts. Spending time observing how domain experts perform their tasks can reveal subtle interactions and data flows that might not be immediately obvious from structured data alone. Understanding the raw data format and characteristics. Once you have a conceptual understanding of the domain, the next step is to examine the raw data itself. This involves preliminary data exploration to understand its structure, quality, and potential for transformation into a graph. Consider a common scenario in recruitment. You have a data set of candidates and a separate data set of referrals. A referral typically links a referrer, an existing employee or candidate, to a referred candidate. Let's simulate a raw data set to illustrate this. We'll use the code snippet library, a fundamental tool for data manipulation in Python. Code is not spoken. To get code, please see the link in description or bio. This code snippet sets up two code snippet objects, code snippet and code snippet, which mimic the structure of raw data you might encounter. Code snippet contains information about individual candidates, while code snippet logs each referral event. Linking a code snippet to a code snippet. The code snippet method displays the first few rows, giving an immediate sense of the data's format and columns. Initial data exploration and deriving insights. After loading the raw data, the next step is to perform basic exploratory data analysis, EDA. This helps in understanding the scale, distribution, and potential relationships within the data. Code is not spoken. To get code, please see the link in description or bio. The code snippet method provides a concise summary of a data frame, including the number of entries, data types of each column, and non-null values. This is crucial for identifying missing data or incorrect data types early on. Following this, we use code snippet to count unique identifiers and code snippet to count rows, which directly maps to the number of candidates and number of referrals mentioned in typical preliminary analyses. The calculated ratio, like 12,239 referrals / 1,933 candidates in a real scenario, provides a quick measure of network density. Interpreting preliminary analysis for GNNs. The preliminary analysis, such as the number of unique candidates and referral events, provides critical insights for designing your graph model and understanding its potential for GNNs. For instance, if we found 10 unique candidates and 12 referral events in our simulated data. This means nodes, we have 10 potential candidate nodes, code snippet. Edges, we have 12 potential referral edges. Ratio A, referral to candidate ratio of code snippet suggests that, on average, each candidate is involved in slightly more than one referral event. Why does this ratio suggest an interconnected network and its implications for GNNs? A ratio significantly greater than 1, as in the real-world example of 12,239 referrals / 1,933 candidates, is almost equal to 6.33 referrals per candidate, implies that candidates are not isolated entities. Instead, many candidates are either referring others, being referred by others, or both. This indicates a rich, multifaceted relationship structure where information might flow through multiple hops. This interconnectedness is precisely what GNNs excel at modeling. Rich relational features. The existence of many edges means there's a wealth of relational information to leverage. GNNs can learn representations, embeddings, for nodes that incorporate not just their individual attributes, e.g., candidate status, location, but also the attributes of their neighbors and the structure of their connections. Community detection. A dense network suggests the potential for communities or clusters of highly interconnected candidates, e.g., a group of employees who frequently refer each other, or candidates from the same professional network. GNNs are excellent for identifying such structures. Link prediction. Given the existing connections, a GNN could be trained to predict new, unobserved referrals. Node classification / regression. The learned embeddings can then be used for tasks like predicting a candidate's likelihood of being hired, classification, or their salary expectation, regression, leveraging the network context. Need for scalable graph algorithms. A highly interconnected network, especially at scale, necessitates efficient graph construction and GNN algorithms that can handle numerous nodes and edges without excessive computational cost. This early understanding helps in selecting appropriate GNN architectures later. Formulating key questions and challenges. The ultimate goal of this preliminary phase is to translate domain and data insights into concrete questions that a GNN model could answer. These questions define the scope and objectives of your project. For the recruitment referral use case, link prediction. Given a candidate and a referrer, what is the likelihood of a successful referral? Or, who is the best person to refer a specific job opening to? Node classification. Which candidates are most likely to be hired based on their referral network? Or, which referrers are most effective at generating high-quality candidates? Community detection. Are there clusters of candidates / referrers that represent specific professional networks or departments? Graph classification. Less common here. Can we identify patterns in referral networks that indicate a healthy versus unhealthy recruitment pipeline? Examples for different industries. Supply chain. Domain questions. Which suppliers are critical bottleneck? X. How does a disruption at one supplier impact downstream operations? Which products are frequently shipped together? GNN questions. Predict the risk of delay for a specific shipment based on its path through the supply chain network. Link prediction / node regression. Identify groups of interdependent suppliers and customers. Community detection. Healthcare, drug discovery / interaction. Domain questions. Which genes are associated with a particular disease? What are the potential side effects of combining two drugs? Which drug targets are most promising for a new therapy? GNN questions. Predict novel drug-target interactions. Link prediction. Identify drug compounds with similar therapeutic effects based on their molecular structure and interaction networks. Node classification / graph similarity. Fraud detection. Domain questions. How do fraudsters collude? What patterns indicate fraudulent transactions? Are there unusual connections between accounts or transactions? GNN questions. Identify fraudulent entities, users, transactions, based on their connections within a financial network. Node classification. Detect suspicious transaction rings or money laundering schemes. Community detection / graph classification. By systematically exploring the domain and raw data, and then translating observations into concrete questions, you lay a solid foundation for designing an effective and impactful graph model. This rigorous initial phase prevents common pitfalls, such as building models that solve the wrong problem or are based on flawed assumptions about the underlying data. Constructing the graph dataset and schemas. Designing the underlying data structure for any machine learning project is paramount, and for graph neural networks, GNNs, this involves carefully constructing a graph dataset and defining its schema. A well-designed graph schema is the blueprint that guides the transformation of raw data into a structured graph, ensuring data integrity, facilitating efficient querying, and ultimately impacting the performance and interpretability of your GNN models. Understanding graph dataset components. Before diving into schema design, it's crucial to solidify the fundamental components of a graph dataset. Nodes, vertices. Nodes represent entities within your domain. Each node typically has a code snippet or code snippet that categorizes it and a set of code snippet that describe its attributes. Labels. A node's label defines its type, e.g., code snippet, code snippet, code snippet. A node can have multiple labels, allowing for flexible categorization. Properties. These are key value pairs associated with a node, providing specific details. For example, a code snippet node might have properties like code snippet, code snippet, code snippet. Edges, relationships. Edges represent connections or relationships between nodes. Like nodes, edges also have a code snippet and can possess code snippet. Types. An edge's type defines the nature of the relationship, e.g., code snippet, code snippet, code snippet. Direction. Edges are typically directed, indicating the flow of the relationship, e.g., code snippet. While some graph systems support undirected edges, most conceptual models benefit from explicit directionality. Properties. Edge properties describe attributes of the relationship itself. For instance, an code snippet edge might have a code snippet property, or a code snippet edge could have a code snippet property. Graph structures. Homogeneous versus heterogeneous. The complexity and diversity of node labels and edge types dictate whether a graph is considered homogeneous or heterogeneous. Homogeneous graphs. These graphs consist of a single node label and a single edge type. For example, a social network where all nodes are code snippet and all edges are code snippet. While simpler, they are less common for complex real-world problems. Heterogeneous graphs. These graphs feature multiple node labels and/or multiple edge types. The whole staffing example will inherently lead to a heterogeneous graph, as we have code snippet, code snippet, code snippet nodes, and relationships like code snippet, code snippet, code snippet. Most real-world applications requiring rich relational data will leverage heterogeneous graphs. Property graphs versus RDF graphs. Two prominent graph data models are property graphs and RDF, Resource Description Framework, graphs. Understanding their differences is crucial for conceptual modeling. Property graphs. This is the most common model in analytical and transactional graph databases. As described above, they allow nodes and edges to have arbitrary key value properties. This flexibility makes them highly expressive for modeling complex domains. Example, property graph representation for a candidate. Imagine a code snippet named Alice with specific skills and experience. In a property graph, this would be represented as a node with a label and properties. Code is not spoken. To get code, please see the link in description or bio.python. Import networks as NX. Initialize an empty graph. G_A equals NX.digraph. Add candidate nodes. G_A add _node. C001. Label equals candidate. Name equals Alice Smith. Email equals alice@email.com. Experience_years equals 5. G_A.add_node. C002. Label equals candidate. Name equals Bob Johnson. Email equals bob@email.com. Experience_years equals 3. Add job nodes. G underscore A underscore node, J001. Label equals job. Title equals data scientist. Company underscore name equals Acme Corp. G underscore A underscore node, J002. Label equals job. Title equals software ENG. Company underscore name equals Beta Incorporated. Add skill nodes. G underscore underscore node Python. Label equals skill. G underscore underscore node SQL. Label equals skill. G underscore underscore node ML. Label equals skill. G underscore underscore node Java. Label equals skill. G underscore underscore node cloud. Label equals skill. G underscore underscore node statistics. Label equals skill. Add location nodes. G underscore underscore node New York. Label equals location. G underscore underscore node San Fran. Label equals location. Code is not spoken. To get code, please see the link in description or bio.python. Add edges and their properties. Candidate skills. G underscore A underscore edge C001 Python. Type equals has underscore skill. Proficiency underscore level. Equals expert. G underscore A underscore edge C001 SQL. Type equals has underscore skill. Proficiency underscore level equals advanced. G underscore A underscore edge C001 ML. Type equals has underscore skill. Proficiency underscore level equals intermediate. G underscore A underscore edge C002 Java. Type equals has underscore skill. Proficiency underscore level equals expert. G underscore A underscore edge C002 SQL. Type equals has underscore skill. Proficiency underscore level equals intermediate. Job requirements. G underscore edge J001 Python. Type equals requires underscore skill. Required underscore level equals advanced. G underscore edge J001 ML. Type equals requires underscore skill. Required underscore level equals intermediate. G underscore edge J001 Statistics. Type equals requires underscore skill. Required underscore level equals basic. G underscore edge J002 Java. Type equals requires underscore skill. Required underscore level equals expert. G underscore edge J002 Cloud. Type equals requires underscore skill. Required underscore level equals advanced. Code is not spoken. To get code, please see the link in description or bio.python. Candidate locations. G underscore edge C001 New York. Type equals lives underscore. G underscore edge C002 San Fran. Type equals lives underscore. Job locations. G underscore edge J001 New York. Type equals located underscore at. G underscore edge J002 San Fran. Type equals located underscore at. Applications. G underscore edge C001 J001. Type equals applies underscore TO. Date underscore applied equals 2023-10-26. G underscore edge C002 J002. Type equals applies underscore TO. Date underscore applied equals 2023-10-25. Example of accessing data. Print G underscore A dot nodes C001. Print G underscore A dot edges C001 Python. Code is not spoken. To get code, please see the link in description or bio.python. Import networks as NX. Initialize an empty graph. G underscore B equals NX dot digraph. Add candidate nodes with embedded pro. Pertize. G underscore B underscore node C001. Label equals candidate. Name equals Alice Smith. Email equals alice@email.com. Experience underscore years equals 5. Skills sad face Python, SQL, ML. Location equals New York. G underscore B dot add underscore node C002. Label equals candidate. Name equals Bob Johnson. Email equals bob@email.com. Experience underscore years equals 3. Skills sad face Java, SQL. Location equals San Fran. Code is not spoken. To get code, please see the link in description or bio.python. Add job nodes with embedded properties. G_add_node, J001, label equals job, title equals data scientist, company_name equals Acme Corp. Required skills sad face Python, ML, statistics, location equals New York. G_b_node, J002, label equals job, title equals software ENG, company_name equals Beta Incorporated. Required skills sad face Java, cloud, location equals San Fran. Add application edges. G_b_edge, C001, J001, type equals applies_to, date_applied equals 2023-10-26. G_b_edge, C002, J002, type equals applies_to, date_applied equals 2023-10-25. Example of accessing data. Print G_b.nodes, C001. Code is not spoken. To get code, please see the link in description or bio.python. Import networks as NX. Initialize an empty graph. G_c equals nx.digraph. Add candidate nodes with embedded location. G_c.add_node, C001. Label equals candidate. Name equals Alice Smith. Email equals alice@email.com. Experience_years equals 5. Location equals New York. G_c.add_node, C002. Label equals candidate. Name equals Bob Johnson. Email equals bob@email.com. Experience_years equals 3. Location equals San Fran. Add job nodes with embedded location and company. G_c.add_node, J001. Label equals job. Title equals data SC. Scientist. Location equals New York. Company_name equals Acme Corp. G_c.add_node, J002. Label equals job. Title equals software ENG. Location equals San Fran. Company_name equals Beta Incorporated. Add skill nodes as an option A. G_c.add_node, Python. Label equals skill. G_c.add_node, SQL. Label equals skill. G_c.add_node, ML. Label equals skill. G_c.add_node, Java. Label equals skill. G_c.add_node, cloud. Label equals skill. G_c.add_node, statistics. Label equals skill. Code is not spoken. To get code, please see the link in description or bio.python. Add edges for skills as an option A. G_c.add_edge, C001, Python. Type equals has_skill. Proficiency level equals expert. G_c.add_edge, C001, SQL. Type equals has_skill. Proficiency level equals advanced. G_c.add_edge, C001, ML. Type equals has_skill. Proficiency level equals intermediate. G_c.add_edge, C002, Java. Type equals has_skill. Proficiency level equals expert. G_c.add_edge, C002, SQL. Type equals has_skill. Proficiency level equals intermediate. Add edges for job requirements as an option A. G_c.add_edge, J001, Python. Type equals requires _skill. Required level equals advanced. G_c.add_edge, J001, ML. Type equals requires _skill. Required level equals intermediate. G_c.add_edge, J001. Statistics. Type equals requires _skill. Required level equals basic. G_c.add_edge, J002. Java. Type equals requires _skill. Required level equals expert. G_c.add_edge, J002. Cloud. Type equals requires _skill. Required level equals advanced. Add application edges as an option B. G_c.add_edge, C001. J001. Type equals applies underscore TO, date underscore applied equals 2023-10-26. G underscore C add underscore EC002, J002, type equals applies underscore TO, date underscore applied equals 2023-10-25. Example of accessing data. Print G underscore C dot nodes, J001. Code snippet Canada code, snippet job code, snippet applies underscore TO code, snippet job code, snippet skill code, snippet requires underscore skill code, snippet skill code, snippet has underscore skill. Then, compare the candidate's skills to the job's required skills. This process helps identify if the chosen schema makes it straightforward or overly complex to retrieve the necessary contextual information for your GNN. If a simple query becomes convoluted, it might indicate a suboptimal schema design. 3. Review with stakeholders. Present the conceptual schema, e.g., using an ERD, to domain experts or business stakeholders. Their feedback is invaluable in ensuring the schema accurately reflects the real-world business logic and requirements. By rigorously testing your graph schema at the design stage, you can catch potential issues early, leading to a more robust, efficient, and effective graph dataset for your GNN applications. Creating instance models. After defining a comprehensive graph schema, the next crucial step in graph data modeling is to create an instance model. An instance model is a small, concrete realization of your abstract graph schema, populated with a representative subset of your actual raw data. It serves as a tangible prototype of your intended graph, allowing you to validate the schema's design, identify potential issues, and ensure that your real-world data can be accurately mapped to the defined graph structure. Purpose of an instance model. An instance model acts as a bridge between the theoretical schema and the practical implementation. Its primary purposes include 1. Schema validation. It allows you to test if your schema accurately captures the nuances of your data and use case. By attempting to map real data, you can uncover ambiguities, missing properties, incorrect cardinalities, or problematic relationships that were not apparent during the abstract design phase. 2. Debugging data mappings. It helps in debugging the rules and logic for transforming raw data into graph elements, nodes, edges, and properties. This is especially important for complex datasets where a direct one-to-one mapping might not be obvious. 3. Representative dataset for testing. A well-crafted instance model can serve as a small, representative dataset for initial testing of graph processing algorithms, queries, or even for training and evaluating graph neural networks, GNNs, in a controlled environment before scaling up to the full dataset. 4. Communication and collaboration. A concrete instance model, often visualized, provides a clear and unambiguous example of the graph structure, facilitating discussions and understanding among technical teams, domain experts, and stakeholders. Steps in creating an instance model. Creating an instance model is an iterative process that involves selecting a small dataset, mapping it to your schema, and then instantiating and validating the resulting graph structure. 1. Identify core entities and relationships from raw data. Before you can build an instance model, you must have a clear understanding of your raw data and how it relates to the conceptual entities and relationships defined in your schema. This step builds directly on the code snippet section and the code snippet section. You should know which parts of your raw data will become nodes, which will become edges, and what properties each will possess. Consider a simple e-commerce scenario where we have data about code snippet and their code snippet. Example tabular data. Let's assume our raw data is initially in a tabular format, such as CSV files or database tables. Code snippet. Code is not spoken. To get code, please see the link in description or bio. Code snippet. Code is not spoken. To get code, please see the link in description or bio. Our schema might define nodes, code snippet, properties, code snippet, code snippet, code snippet, properties, cod. E-snippet, code snippet. Edge, code snippet, from code snippet to code snippet. 2. Select a representative subset of data. It's impractical and unnecessary to build an instance model from your entire dataset. Instead, choose a small, representative subset of your raw data that covers all major node types, edge types, and typical property values. This subset should ideally include examples of each node type with all their expected properties, examples of each edge type demonstrating their source and target node types, cases that might test cardinality constraints, e.g., a user with multiple transactions, any edge cases or special conditions you anticipate. For our example, the 3 users and 3 transactions shown above are a good representative subset. 3. Map raw data to schema elements, nodes, edges, properties. This is the core mapping step. You explicitly define how each piece of raw data translates into a graph element. Each row in code snippet becomes a code snippet node. Code snippet becomes the node's unique identifier. Code snippet and code snippet become properties of the code snippet node. Each row in code snippet becomes a code snippet node. Code snippet becomes the node's unique identifier. Code snippet and code snippet become properties of the code snippet node. The code snippet column in code snippet links a code snippet back to the code snippet who performed it. This implies a code snippet edge from the code snippet node to the code snippet node. 4. Instantiate the graph data structure. This step involves programmatically creating the graph using a chosen graph library or database. For educational purposes, Python's code snippet is an excellent choice as it's lightweight and widely used for graph manipulation. First, we'll import the necessary library and initialize an empty graph. We'll use code snippet because it allows for multiple edges between the same pair of nodes, though not strictly necessary for this simple example. It's a good general choice for complex graphs and supports directed edges, which is typical for relationships like performed. Code is not spoken. To get code, please see the link in description or bio. Here, code snippet creates an empty graph object. This object will store our nodes, edges, and their associated properties. The choice of graph type, code snippet, code snippet, code snippet, code snippet, depends on whether your relationships are directed or undirected, and if multiple relationships of the same type can exist between 2 nodes. Next, we'll represent our sample tabular data in a Python-friendly format, such as lists of dictionaries. This makes it easy to iterate and extract properties. Code is not spoken. To get code, please see the link in description or bio. These lists of dictionaries directly mirror the rows in our conceptual code snippet and code snippet files, making the mapping clear. Now, we add the code snippet nodes to our graph. Each user's code snippet will be the node identifier, and their code snippet will be stored as node properties. We also add a code snippet property to explicitly define the node type, which is crucial for schema validation. Code is not spoken. To get code, please see the link in description or bio. The code snippet method takes the node identifier as the first argument. Subsequent keyword arguments, code snippet, are used to store arbitrary data, properties, associated with that node. We explicitly set a code snippet to denote the node's type, which is a common practice in graph databases and libraries for categorizing nodes. Finally, we add the code snippet nodes and the code snippet edges that link users to their transactions. Code is not spoken. To get code, please see the link in description or bio. Here, for each transaction, we first create a code snippet node, similar to how we created code snippet nodes. Then, we use code snippet to create the relationship. This method takes the source node ID, the target node ID, and then any properties for the edge itself. In this case, we add a code snippet property to distinguish the relationship, and also include code snippet as an edge property, demonstrating how properties can reside on relationships. At this point, our code snippet graph code snippet is a fully instantiated instance model based on our sample data and schema. 5. Visualize and review. While not directly code-based, visualizing the instance model is a powerful step. Tools like NetworkX's built-in drawing functions or dedicated graph visualization software, e.g., Gephi, Neo4j Bloom, if using Neo4j, can render your graph. This visual representation, similar to figure 8.6 in your textbook, if applicable, allows for quick visual inspection of connectivity. Are all expected nodes connected? Are there isolated nodes? Relationship direction. Are edges pointing the correct way? Node/edge types. Are the different types of nodes and edges visually distinct and correctly represented? Data integrity. Do the properties appear as expected? Visual review helps catch conceptual errors that might be hard to spot in code or raw data alone. 6. Validate against schema rules. This is arguably the most critical step. Once the instance model is created, you must validate it against the rules defined in your graph schema. This involves checking node properties, edge types, cardinalities, and any other constraints. This step explicitly connects the abstract schema rules to their concrete enforcement. Let's define a simple Python dictionary to represent some of our schema rules. Code is not spoken. To get code, please see the link in description or bio. This code snippet dictionary outlines some basic rules, required properties for node types, expected ID prefixes, and allowed relationships for edges, including their source/target types and required edge properties. Now, let's write a Python function to perform basic validation checks on our code snippet G. Graph against these code snippet. Code is not spoken. To get code, please see the link in description or bio. This code snippet function iterates through all nodes and edges in the code snippet graph. For each, it checks if its type, code snippet for nodes, code snippet for edges, exists in our code snippet. It then proceeds to check if all code snippet are present. For edges, it also validates if the source and target node types match the schema. This function can be extended to include more complex rules like property data types, value constraints, or cardinality checks. Let's run the validation on our code snippet graph created earlier. Code is not spoken. To get code, please see the link in description or bio. Running this code should output validation passed, indicating that our instance model correctly conforms to the defined schema rules. Demonstrating a failed instance model. To truly understand the value of validation, let's create an instance model that violates our schema and observe the validation errors. We'll simulate a scenario where code snippet node is missing a required property, code snippet. Code is not spoken. To get code, please see the link in description or bio. This output should show validation failed as expected with the following errors. Node U3 type, user, missing required property, city. This demonstrates how the instance model and validation process can effectively catch schema violations. 7. Refine schema, iterative process. If the validation step reveals errors or inconsistencies, it means your schema needs refinement. This is an iterative process. 1. Identify the discrepancy. Pinpoint whether the issue is with your raw data, your mapping logic, or the schema definition itself. 2. Adjust. If the data is incorrect, you might need data cleaning or pre-processing. If the mapping logic is flawed, correct your transformation rules. If the schema is too restrictive or too loose, modify node/edge types, properties, or constraints. 3. Reinstantiate and revalidate. Apply the changes, recreate the instance model, and run the validation checks again. This cycle continues until your instance model successfully validates against your schema, giving you confidence that your schema design is robust and accurate for your data. Common pitfalls and best practices. Common pitfalls. Selecting non-representative data. Choosing a subset that doesn't include all complexities or edge cases can lead to a false sense of security during validation. Overlooking edge cases. Failing to include data that tests boundary conditions or unusual scenarios, e.g., a user with no transactions or a transaction with multiple associated users if allowed by schema. Insufficient validation. Relying only on visual inspection or basic checks. Missing deeper validation of property data types, value ranges, or complex cardinality rules. Ignoring the iterative nature. Treating schema design and instance modeling as a one-off task rather than a continuous refinement process. Best practices. Start small and grow. Begin with the absolute minimum data required to represent your core schema. then progressively add more complex scenarios. Automate validation. Implement programmatic validation checks like the code snippet function. This ensures consistency and makes the process repeatable. Document mapping rules. Clearly document how each piece of raw data maps to graph elements. This is crucial for maintainability and for others to understand your model. Involve domain experts. Regularly review your instance model and schema with domain experts to ensure it accurately reflects the real-world domain. Use version control. Keep your schema definitions, instance model code, and validation scripts under version control. This tracks changes and facilitates collaboration. Consider tooling. Leverage graph databases like Neo4j, Amazon Neptune, or specialized graph libraries like PyTorch Geometric for GNNs early on, as they often have built-in schema enforcement or validation capabilities. By diligently creating and validating instance models, you significantly de-risk your graph data project, ensuring that your graph schema is well-designed, functional, and ready for large-scale data ingestion and advanced analytics, including GNN training. Testing and refactoring. The development of robust and effective graph data models, especially those intended for graph neural network, GNN, applications, is not a linear process. It is an iterative cycle of design, implementation, testing, and refinement. This section delves into the critical role of testing and refactoring, emphasizing how these practices ensure data integrity, consistency, and suitability for downstream machine learning tasks, while actively mitigating technical debt. The iterative nature of graph model development. Graph modeling, much like software development, benefits immensely from an iterative approach. Initial conceptual schemas are hypotheses about how data should be structured. These hypotheses must be rigorously tested against actual data and use cases. Testing reveals inconsistencies, missing information, or logical flaws in the model. Based on these findings, the model is refactored, its internal structure improved without altering its external behavior or the core information it represents. This continuous feedback loop ensures that the final graph model accurately reflects the domain, meets application requirements, and provides a stable foundation for GNNs. Types of tests for graph data models. Testing a graph data model involves validating both the schema, the blueprint, and the instance model, the concrete realization with actual data. These tests ensure the data adheres to expected structures, types, and constraints. We will use Python with the code snippet library to demonstrate these tests, as it provides a flexible environment for graph manipulation and querying. First, let's establish a simple instance model based on our whole staffing recruiting firm example to serve as our test subject. This model will represent code snippet nodes, and code snippet relationships. Code is not spoken. To get code, please see the link in description or bio. This initial graph code snippet contains some intentional errors, e.g., code snippet has code snippet has code snippet as a string, which we will uncover with our tests. Node attribute verification. These tests ensure that nodes possess the expected attributes, that those attributes have the correct data types, and that their values fall within valid ranges or sets. Code is not spoken. To get code, please see the link in description or bio. This code iterates through every node, checks its code snippet attribute, and then validates the presence and data type of other attributes specific to that node type. It also includes checks for valid enumerated values, e.g., active or inactive for code snippet status. The output immediately highlights that code snippet is missing code snippet and code snippet has an incorrect code snippet type. Edge type and relationship verification. These tests ensure that relationships, edges, between nodes conform to the schema's defined types and properties, and that their directionality is core. CT. Code is not spoken. To get code, please see the link in description or bio. This segment checks if each edge has a defined code snippet attribute, and if that type matches a predefined schema. It then validates that the source and target nodes of the edge have the correct types as per the schema, e.g., code snippet must go from code snippet to code snippet. Finally, It verifies mandatory edge properties and checks for undirectedness where specified. Unique ID validation. While NetworkX uses node identifiers as unique keys implicitly, in graph databases, explicit unique IDs are crucial. This test ensures that all nodes and relationships have distinct identifiers, preventing data corruption and ensuring correct data retrieval. Code is not spoken. To get code, please see the link in description or bio. This conceptual test shows how to check for duplicate unique identifiers. While NetworkX handles node uniqueness by default, real-world graph databases often have explicit code snippet or code snippet properties that need validation. The example simulates this by adding a code snippet property and then checking for duplicates. Network structure validation. Understanding and validating the graph structure is paramount for GNNs, as they heavily rely on connectivity patterns. Code is not spoken. To get code, please see the link in description or bio. This suite of tests uses NetworkX functions to check for graph connectivity. Are all parts of the graph reachable? Degree. Distributions. Identifying nodes with unusually high or low connections, including isolated nodes, and cycles, which can indicate problematic circular dependencies in certain contexts. It will reveal that code snippet is isolated. Edge cases and specific queries. Beyond general structural validation, it's crucial to query for specific edge cases or patterns that might indicate issues or provide valuable insights. Code is not spoken. To get code, please see the link in description or bio. These examples demonstrate how to construct specific queries to identify potential issues or unusual data patterns. For instance, finding persons who applied for no jobs or job postings with no applicants can highlight data quality issues or gaps in the recruiting process. Interpreting test results and identifying flaws. Each fail or warning from the tests indicates a deviation from the expected graph model. Interpreting these results is crucial for deciding on the next steps. 1. Data inconsistency. The data itself does not conform to the schema. Example: code snippet missing code snippet having string code snippet. The schema expects an integer/float, but the data source provided code snippet or string. Remedy: data cleaning, pre-processing, or fixing the data ingestion pipeline. 2. Schema flaw. The conceptual or system schema itself is inadequate or incorrect for the real-world domain or application needs. Example: discovering that code snippet I, initially a list property, needs to be its own node type, code snippet, with relationships to allow complex querying or GNN feature engineering. Remedy: refactoring the schema. 3. Data generation logic issue. The process that transforms raw data into the graph instance model has a bug. Example: a script incorrectly assigns a string to a numeric attribute, or fails to create an expected edge. Remedy: debugging and fixing the data generation code. 4. Implicit assumption uncovered. The tests reveal an unstated assumption about the data that was not captured in the schema or understood by the modelers. Example: expecting all persons to have applied for at least one job, but finding isolated code snippet nodes. This might be acceptable, or it might signal a need to enrich the data or revise the schema to allow for unengaged persons. Remedy: reevaluate the conceptual model, potentially refactor or adjust data pipeline. Refactoring graph data models. Refactoring is the process of restructuring an existing body of code or data without changing its external behavior. In graph modeling, it means improving the internal structure of your schema or instance generation logic to make it cleaner, more robust, more expressive, and better suited for its ultimate purpose, e.g., GNNs, without altering the core information it represents. Schema refactoring versus instance creation logic refactoring. It's vital to distinguish between 1. Schema refactoring, modifying the blueprint of your graph model. This involves changing node types, edge types, properties, and their constraints. This is a fundamental change and often requires re-ingesting or transforming existing data. 2. Instance creation logic refactoring, modifying the code or process that transforms raw data into a graph instance based on an existing schema. This doesn't change the schema itself, but improves how data maps to it. Test failures can inform both types of refactoring. For example, if a code snippet test fails due to a code snippet value, e.g., code snippet, it might trigger a refactor of the instance creation logic to handle missing data, e.g., impute, skip, or use a default. If a code snippet test reveals that a simple property is actually a complex entity that needs its own node, e.g., code snippet as a list, it triggers a schema refactoring. Common refactoring patterns for graph data models. Let's explore some common refactoring patterns, illustrating with before and after scenarios and how test results might prompt these changes. 1. Attribute to node conversion. Scenario: you initially model certain complex attributes as simple properties on a node. However, testing or future use cases, like GNNs that need features from these attributes or queries that need to traverse them, reveal that these attributes are entities in their own right, with their own properties or relationships. Example: code snippet skills. Initial schema before refactoring. Code snippet nodes have a property code snippet, which is a list of strings, e.g., code snippet. Test result: queries for job postings requiring both Python and SQL are cumbersome. GNNs struggle to leverage individual skills as distinct features or relate skills to other entities, e.g., code snippet. Refactored schema. After refactoring, introduce a new node type code snippet and an edge type code snippet from code snippet to code snippet. Code snippet. Code snippet nodes can have their own properties, e.g., code snippet. Code example: data transformation for attribute to node conversion. Let's assume our initial code snippet had a code snippet list property. Code is not spoken. To get code, please see the link in description or bio. This refactoring allows skills to be first-class entities. A GNN can now learn embeddings for individual skills, and queries can easily find all jobs requiring Python or all persons possessing SQL if we added code snippet edges from code snippet to code snippet. 2. Edge property refinement. Scenario: an important piece of information is currently modeled as a node property or implicitly within an edge, but it logically belongs on the edge itself to provide context to the relationship. Example: code snippet property versus code snippet. Initial schema: code snippet has an code snippet property. Test result: while simple, F code snippet itself needs to be a node for complex temporal analysis or linking to code snippet nodes. The property model is limiting. Refactored schema: code snippet node, and code snippet relationship with code snippet property. Code snippet, node with code snippet property. Or, more commonly, if code snippet is just a simple value, but the date of an application is important. Code snippet with code snippet property, code snippet. Our initial code snippet already has a code snippet property, which is a good design choice. This is less about transforming code snippet to a node and more about ensuring that properties that describe the relationship itself are placed on the edge. Our initial code snippet edge having a code snippet property is a good example of this pattern. If code snippet was a node property on code snippet, it would be refactored to an edge property on code snippet. 3. Schema normalization/denormalization. Scenario: balancing query complexity, data redundancy, and GNN feature engineering needs. Normalization: breaking down a complex node or relationship into simpler, more atomic components to reduce redundancy and improve data integrity. Similar to attribute to node conversion, but more general. Test result: redundant data, difficulty in updating or querying specific subparts of a complex attribute. Denormalization: combining entities or properties to reduce joins/traverse. ALS for specific, frequent queries or to simplify feature engineering for GNNs, potentially at the cost of redundancy. Test result: performance bottlenecks for common queries, GNNs requiring too many hops to gather relevant features. Example, denormalizing code snippet department into code snippet node. Normalized, conceptual code snippet, node with code snippet properties. Test result, to get a jobs department name. You always need a 2-hop query. For many GNNs, this might mean more layers or complex message passing if code snippet is a crucial feature. Denormalized, refactored code snippet has a code snippet property. Test result, simpler queries for department name. Direct feature for GNNs. Downside, if code snippet itself has many properties or relationships, those are lost. The choice between normalization and denormalization depends heavily on the specific use cases and the GNN architecture. Testing can help identify where the current schema impedes performance or feature extraction. Handling test failures that indicate fundamental flaws. Sometimes, test failures are not minor data inconsistencies, but point to a fundamental misunderstanding of the domain or a poor conceptual model. Example, if code snippet relationships frequently exist from code snippet to code snippet, the reverse of what's expected, it might mean the initial conceptual model of who applies for what was flawed or the data source itself. F is inverted. Strategy. In such cases, the refactoring goes beyond simple schema changes. It requires revisiting the conceptual model, potentially re-engaging with domain experts, and redesigning large parts of the graph. This is where the iterative process is most crucial. Early testing prevents these fundamental flaws from propagating. Technical debt and GNN performance. Technical debt in graph data modeling arises when suboptimal design choices are made, often due to time constraints, incomplete understanding, or lack of rigorous testing. This debt manifests as increased maintenance overhead, debugging data inconsistencies, fixing broken queries, poor data quality, inaccurate or inconsistent data, leading to unreliable insights, difficult feature engineering. Extracting meaningful features for GNNs becomes complex and error-prone due to convoluted data structures. Suboptimal GNN performance. Incorrect feature representation. If the model doesn't accurately capture entities or relationships, the GNN's node and edge features will be misleading. For instance, if code snippet are just a string property, the GNN cannot effectively differentiate or relate individual skills. Graph structure mismatch. If the graph structure doesn't accurately reflect real-world relationships, the GNN's message passing mechanism will propagate incorrect information. An isolated code snippet node might be excluded from relevant social network analysis if the code snippet relationship is incomplete. Data sparsity/density issues. Untested data might have unexpected sparsity, e.g., too few connections, or density, e.g., supernodes, which could destabilize GNN training or lead to poor generalization. Training instability. Poor data quality can lead to GNNs failing to converge, overfitting, or producing erratic results. Proper testing and refactoring are proactive measures against technical debt. By systematically validating the graph model, you ensure that the GNN operates on a clean, consistent, and semantically rich data foundation. Furthermore, test failures can inform decisions about GNN architecture or feature engineering. For example, if testing reveals many isolated nodes, the GNN might need strategies to handle disconnected components, or perhaps a different graph pooling mechanism. If certain relationships are very sparse, it might suggest that the GNN needs to rely more on node features than structural features, or that the edge types need aggregation. If a property consistently has missing values, it informs a decision on how to impute or handle that missingness during feature matrix creation for the GNN. Automated testing considerations. While manual checks are useful during development, for production-grade graph models, automated testing is essential. This involves test suites, collections of tests that can be run automatically, e.g., using code snippet in Python. Continuous integration/continuous deployment, CI/CD integrating GraphD. Data validation into automated CI/CD pipelines ensures that every change to the data generation logic or schema is tested before deployment. Custom scripts, developing domain-specific scripts that query the graph, using Cypher for Neo4j, Sparkle for RDF, or NetworkX/PYG for in-memory graphs, and assert expected conditions. These scripts can run nightly or on data ingestion. Automated tests provide a safety net, catching regressions and ensuring data quality over time, especially as data sources evolve or schemas change. Data pipeline example. Preparing data for graph neural networks, GNNs, is a critical step that bridges raw, often non-graph data with the structured input requirements of GNN frameworks. This process, commonly referred to as a data pipeline, transforms disparate data sources into a cohesive graph representation ready for model training. Building upon the graph schema design and instance modeling discussed previously, this section outlines the conceptual stages of such a pipeline and provides concrete examples of how to implement them. Stages of a GNN data pipeline. A typical data pipeline for GNNs involves several sequential stages, each with specific objectives. 1. Raw data collection. Gathering data from various sources, databases, CSVs, APIs. 2. Data exploration. Understanding the characteristics, quality, and structure of the raw data. 3. ETL, extract, transform load. Extract. Reading the raw data into a processing environment. Transform. Converting raw data into a structured graph format. Nodes, edges, features that adheres to the defined graph schema. This is where the schema's role becomes paramount. Load. Staging the transformed data for the next phase. 4. Pre-processing for GNN frameworks. Converting the general graph representation into specific data structures required by GNN libraries like PyTorch Geometric, PYG, or Deep Graph Library, DGL. This often includes creating features, labels, and data splits. 5. Serialization. Saving the processed graph data in a persistent format for efficient loading during GNN training. Let's explore each stage with practical examples. Stage 1. Raw data collection. The initial stage involves gathering data from its original sources. This data is often in a non-graph format, such as relational database tables, CSV files, JSON documents, or API responses. For our example, we will consider a simple candidate referral network where code snippet contains information about individuals, nodes. Code snippet contains information about referrals between individuals, edges. Code snippet example. Code is not spoken. To get code, please see the link in description or bio. Code snippet example. Code is not spoken. To get code, please see the link in description or bio. Stage 2. Data exploration. Before transforming raw data, it's crucial to explore its characteristics. This stage helps in understanding data types, identifying missing values, assessing data quality, and gaining initial insights that will inform the transformation and pre-processing steps. Common tools for this stage include code snippet for tabular data manipulation and code snippet for basic graph analysis. Let's load our example CSVs into Pandas data frames and perform some initial exploration. Code is not spoken. To get code, please see the link in description or bio. This code snippet loads the code snippet file into a Pandas data frame and then prints its information, code snippet, and the first few rows, code snippet. The snippet method is invaluable for checking data types and identifying non-null counts, which immediately highlights missing values. Code is not spoken. To get code, please see the link in description or bio. Similarly, we explore the code snippet. The code snippet method provides statistical summaries for numerical columns and, with code snippet, for categorical columns as well. For instance, code snippet would show the distribution of code snippet. Insights from exploration. Data types. Ensure columns are interpreted correctly, e.g., code snippet might be an object initially and need conversion to datetime. Missing values. Identify columns with missing data, code snippet. Decide on strategies like imputation or removal. Unique identifiers. Verify that code snippet in code snippet and code snippet slash code snippet in code snippet are consistent and can be used to link entities. Distribution. For numerical features like code snippet, check their range and distribution. For categorical features like code snippet or code snippet, check unique values and their counts. This can reveal potential issues like typos or imbalanced categories. Stage 3. ETL, extract, transform, load. This is the core stage where raw data is converted into a graph representation that aligns with our predefined graph schema. Extract. The extract part is already covered by loading the CSVs into pandas data frames in the exploration stage. Transform. The transform stage is where T magic happens. We map our raw tabular data to the graph schema, identifying nodes, edges, and their respective features. 1. Node transformation. We need to define node features. For our example, code snippet, and code snippet from code snippet can serve as node features. Categorical features like code snippet and code snippet often need to be converted into numerical representations, e.g., one-hot encoding or label encoding. Code is not spoken. To get code, please see the link in description or bio. Here, we use code snippet from code snippet to convert code snippet and code snippet into numerical values. This is a common pre-processing step as GNNs typically expect numerical input features. 2. Edge transformation and graph representations. Edges define relationships between nodes. The code snippet directly provides code snippet and code snippet. We also have in code snippet edge attribute, code snippet that can be encoded. Before we process edges, it's essential to understand common graph data representations. Edge list. This is the most common and often preferred representation for GNN libraries due to its simplicity and efficiency, especially for sparse graphs. It's simply a list of tuples or pairs code snippet. Suitability. Ideal for sparse graphs, most real-world graphs, flexible for adding edge attributes, and directly consumable by most GNN frameworks. Adjacency list. For each node, a list of its neighbors, e.g. code snippet. Suitability, G. Good for iterating through neighbors of a specific node. Less common as primary input for GNN frameworks compared to edge lists, but often used internally or for specific graph algorithms. Adjacency matrix. A square matrix where rows and columns represent nodes, and a non-zero entry at code snippet indicates an edge from node code snippet to node code snippet. 4 unweighted graphs. Entries are typically 0 or 1. 4 weighted graphs. Entries represent edge weights. Suitability. Simple for dense graphs. However, for sparse graphs, most real-world graphs, it's highly inefficient in terms of memory, many zeros, and computation. GNNs generally avoid explicit adjacency matrices for large, sparse graphs. For GNNs, the edge list is generally the most suitable representation because GNN frameworks are optimized to process graph connectivity represented as sparse tensors, which are essentially edge lists. Code is not spoken. To get code, please see the link in description or bio. Here, we encode the code snippet column for our edge features, mapping node IDs to integer indices. GNN libraries typically expect node IDs to be contiguous integers starting from 0. Our code snippet has code snippets starting from 1. We need to create a mapping from original IDs to these contiguous internal indices. Code is not spoken. To get code, please see the link in description or bio. This is a crucial step. GNN frameworks internally represent graphs using tensors where node indices are 0 based in. Decontiguous. By mapping original IDs to these new indices, we ensure compatibility. It's important to collect all unique node IDs present in both the node and edge data to create a comprehensive mapping. Stage 4. Pre-processing for GNN frameworks. After transforming the data into a general graph representation, nodes with features, edges with features, and integer indices, the next step is to convert this into the specific data structures used by GNN libraries. We'll focus on PyTorch Geometrics code snippet object, which is a common target for GNN data pipelines. A code snippet object in PyTorch geometric typically holds the following attributes. Code snippet, node feature matrix with shape code snippet. Code snippet, graph connectivity in COO format with shape code snippet. This is our edge list. Code snippet, edge feature matrix with shape code snippet. Code snippet, target to be used for supervised learning, e.g., node-level labels, graph-level labels. Shapecode snippet or code snippet. Code snippet, code snippet, code snippet, Boolean mask for data splitting. Let's construct a code snippet object using our process data frames. Code is not spoken. To get code, please see the link in description or bio. We select the relevant numerical and encoded categorical features from our code snippet to form the node feature matrix code snippet. It's converted to a code snippet of code snippet type, as typically required by PyTorch models. Code is not spoken. To get code, please see the link in description or bio. The code snippet tensor represents the graph's connectivity. It's a code snippet tensor where the first row contains source node indices and the second row contains target node indices. It's crucial that these indices are the contiguous zero-based indices we created earlier. Code is not spoken. To get code, please see the link in description or bio. If your graph has edge features, they are collected into an encode snippet tensor. Code is not spoken. To get code, please see the link in description or bio. The code snippet tensor holds the labels for your supervised learning task. In this example, we create a binary classification label. Code snippet if the node's role is software engineer, code snippet otherwise. This demonstrates how to derive a target variable from your node attributes. Code is not spoken. To get code, please see the link in description or bio. Finally, we instantiate the code snippet object. PyTorch geometric automatically infers the number of nodes and edges from the provided tensors. We can also check useful properties like whether the graph has isolated nodes or if it's undirected. Data splitting with Boolean masks. For supervised learning tasks, it's crucial to split your data set into training, validation, and test sets. In GNNs, this is often done using Boolean masks directly within the code snippet object, especially for node-level tasks. Each mask is a Boolean tensor of shape code snippet for node CLA. Cification, or code snippet for link prediction. Code is not spoken. To get code, please see the link in description or bio. This code demonstrates how to create code snippet, and code snippet for node-level tasks. These masks are Boolean tensors where code snippet indicates that a node belongs to that specific split. During GNN training, these masks are used to select which node's loss contributes to training, validation, or testing. This approach is highly memory efficient for graph data. Stage 5, serialization. The final stage in the data pipeline is to serialize, save, the processed code snippet object to disk. This prevents the need to rerun the entire pipeline every time you want to train a model, saving significant time and computational resources. PyTorch geometric code snippet objects can be saved and loaded easily using PyTorch's native serialization functions. Code is not spoken. To get code, please see the link in description or bio. This snippet saves the code snippet object to a code snippet file, PyTorch's recommended file extension for saved tensors and objects. The code snippet and code snippet functions handle the serialization and deserialization, respectively. This allows for quick loading of the pre-processed graph data when starting new training runs or experiments. Common challenges and best practices. Building robust data pipelines for GNNs comes with its own set of challenges. Handling missing values. Decide on a strategy imp. Mutation, deletion during the transform stage. The choice depends on the nature of the data and the downstream task. Large data sets. For graphs with millions or billions of nodes/edges, loading the entire graph into memory might not be feasible. Techniques like graph sampling, e.g., neighbor sampling, subgraph extraction, where using specialized distributed graph processing frameworks become necessary. Dynamic graphs. If the graph structure or features change over time, the pipeline needs to be designed to handle temporal updates efficiently, potentially involving time series databases or streaming data processing. Data imbalance. In classification tasks, an imbalanced distribution of labels can lead to biased models. Techniques like oversampling, undersampling, or weighted loss functions might be applied during pre-processing or training. Schema adherence. Throughout the transform stage, consistently ensure that the converted data strictly adheres to the predefined graph schema. This ensures data quality and compatibility with downstream models. Reproducibility and version control. Treat your data pipeline code and configuration files with the same rigor as your model code. Use version control, e.g., Git, for code, and consider data versioning tools for datasets, especially as they evolve. Pipeline automation. Automate the pipeline using workflow management tools, e.g., Apache Airflow, Prefect, Dagster, for production environments, ensuring data freshness and reliability. By systematically addressing each stage and being mindful of these challenges, you can build efficient and reliable data pipelines that provide high-quality graph data for your GNN projects. Raw data. Raw data represents the initial, unprocessed state of information collected from various sources. It is the fundamental input for any data pipeline, including those designed for graph neural networks, GNNs. In the context of GNN project, raw data often contains the seeds of relationships that, once extracted and structured, will form the nodes and edges of a graph. Understanding raw data means recognizing its original format, its typical sources, and the crucial need to address sensitive information before further processing. This initial stage is depicted as the very first step in the overall GNN training process, as shown in the raw data box within Figure 8.1. Refer to the mental model for graph training process diagram. Common sources of raw data. Raw data for GNN projects can originate from diverse sources, each presenting its own unique characteristics and challenges. Relational databases. These are structured databases that store data in tables with predefined schemas. Common examples include customer relationship management, CRM, systems, enterprise resource planning, ERP, systems, or specialized application databases. Data from relational databases often needs to be joined from multiple tables and then transformed into a format suitable for graph representation. Log files. These are sequential records of events generated by applications, servers, or network devices. Log data is often semi-structured or unstructured, containing timestamps, user A, tie-ins, system events, and other operational information. Extracting meaningful relationships from logs typically involves parsing and pattern recognition. APIs, application programming interfaces data, can be retrieved from external services through APIs, which often return data in structured formats like JSON or XML. Unstructured text/documents. This includes emails, articles, social media posts, or research papers. Natural language processing, NLP, techniques are often required to extract entities and relationships from this type of data. Sensor data, time series data from IoT devices, environmental sensors, or industrial machinery can also serve as raw input, potentially forming temporal graphs. For our running example of a recruiting firm, the raw data primarily stems from two main sources. 1. Recommendation logs. These logs record instances where a recruiter recommended a candidate to a specific job or client. Each log entry might contain identifiers for the recruiter, the candidate, the job, the client, and the timestamp of the recommendation. 2. Candidate profiles. These are structured records detailing information about each candidate, such as their unique ID, industry expertise, job preferences, skills, and potentially other demographic or professional attributes. From disparate sources to a unified format, the role of JSON. Before raw data can be effectively used to construct a graph, it often needs to be transformed into a more unified and structured intermediate format. This step simplifies subsequent processing, validation, and graph construction. While various formats like CSV, XML, or Parquet could be used, JSON, JavaScript object notation, is a particularly popular and flexible choice for representing complex, hierarchical data structures. JSON's advantages include readability. Its human-readable text format makes it easy to inspect and understand. Flexibility. It can represent both simple key-value pairs and complex nested objects and arrays, making it suitable for diverse data structures. Widespread support. Most programming languages have built-in support for parsing and generating JSON, facilitating data exchange. Schema-less nature. While a schema can be enforced at the application level, JSON itself doesn't strictly require one, offering flexibility during data exploration and early pipeline stages. Let's consider how the recruiting firm's data, originally perhaps in separate relational tables, might be transformed into a unified JSON structure. Original data structure, conceptual relational tables. Imagine our raw data resides in two simplified relational database tables. Code snippet table. This table holds static information about each candidate. Code snippet code, snippet code, snippet code, snippet code snippet. Code snippet code, snippet code, snippet code, snippet code snippet. Code snippet code snip. T-code snippet code, snippet code snippet. Code snippet code, snippet code, snippet code, snippet code snippet. Code snippet table. This table records each recommendation event. Code snippet code, snippet code, snippet code, snippet code snippet. Code snippet code, snippet code, snippet code, snippet code snippet. Code snippet code, snippet code, snippet code, snippet code snippet. Code snippet code, snippet code, snippet code, snippet code snippet. Transform data structure, JSON. The goal is to consolidate this information into a JSON format where each top-level object represents a primary entity, e.g., a candidate or recommendation event, and contains all relevant attributes, potentially including nested relationships. For our GNN, we might want to represent each candidate as a node and recommendations as edges. The JSON structure can facilitate this by embedding related information. Here is an example of what the raw data, after an initial transformation into JSON, might look like. This structure combines candidate profile information with the recommendations they are involved in, setting the stage for graph construction. This corresponds conceptually to Figure 8.8. Code is not spoken. To get code, please see the link in description or bio. This JSON structure represents a list of candidate objects where each object includes their profile attributes and nested lists of recommendations. They have either code snippet or code snippet. This pre-aggregation of related data simplifies the subsequent graph construction process, loading and parsing raw JSON data. Once raw data is in a JSON format, Python's built-in code snippet module provides straightforward methods for loading and parsing it into Python objects, dictionaries, and lists. First, let's define our sample JSON data as a multi-line string in Python. In a real-world scenario, this data might be read from a file or received over a network. Code is not spoken. To get code, please see the link in description or bio. The code snippet string now holds our structured raw input. The code snippet method is used to parse a JSON string into a Python object. If you're loading from a file, you would use code snippet with a file object. Code is not spoken. To get code, please see the link in description or bio. The output confirms that code snippet is a Python list, and its elements are dictionaries, perfectly mirroring the JSON structure. This parsed data is now ready for subsequent pre-processing steps, such as feature extraction or graph construction. Data privacy, protecting personally identifiable information, PII, an absolutely critical consideration when dealing with raw data, especially in real-world applications, is the protection of personally identifiable information, PII. PII refers to any data that could potentially identify a FIC individual. Examples include names, addresses, phone numbers, social security numbers, email addresses, and even certain combinations of less sensitive data, e.g., zip code, birth date, gender, that, when linked, can uniquely identify someone. Failing to properly protect PII can lead to severe privacy breaches, legal penalties, such as those under GDPR or CCPA, and significant reputational damage. Therefore, it's a best practice to identify and anonymize or pseudonymize PII as early as possible in the data pipeline, ideally at the raw data state itself. Anonymization using hashing. One common technique for anonymizing identifiers is hashing. Hashing is a one-way cryptographic function that transforms an input, e.g., a candidate's name or email, into a fixed-size string of characters called a hash value or digest. Key properties of cryptographic hash functions like SHA-256 include: one way, it's computationally infeasible to reverse the hash to get the original input. Deterministic. The same input will always produce the same hash output. Collision resistant. It's extremely difficult to find two different inputs that produce the same hash output. By replacing original PII, like a candidate's full name or email, with its hash, you can maintain the ability to track unique individuals within your dataset without storing their actual identifiable information. For example, if you need to link a candidate's activity across different datasets, you can use their hashed ID instead of their real ID. Let's illustrate how hashing might be applied to a hypothetical PII field. Code is not spoken. To get code, please see the link in description or bio. In this example, code snippet becomes a long, seemingly random string. If this email appears elsewhere in the dataset, hashing it again will produce the exact same hash, allowing for linkage without exposing the actual email. Code is not spoken. To get code, please see the link in description or bio. This confirms that hashing is deterministic, a crucial property for maintaining data integrity and relationships while anonymizing. Trade-offs and other anonymization techniques. While hashing is effective for pseudonymization, replacing direct identifiers with consistent, non-identifiable tokens, it's important to understand its limitations and consider other techniques. Reversibility. Hashing is one way, but it's not foolproof against all attacks. If the set of possible original values is small, e.g., a list of 10 common last names, an attacker could pre-compute hashes for all possible values and then reverse the hash by looking up the pre-computed table, a rainbow table attack. For highly sensitive data or data with a small domain, salting, adding a random string before hashing, can mitigate this. Data utility. Anonymization methods often involve a trade-off between privacy protection and data utility. Hashing preserves uniqueness but removes the original semantic meaning of the data. Other techniques might reduce data granularity. Other anonymization techniques. Pseudonymization, replacing direct identifiers with artificial identifiers. Hashing is a form of this. Aggregation, combining data points so that individual identities are obscured, e.g., reporting average salary for a group rather than individual salaries. Generalization/suppression, broadening categories, e.g., replacing exact age with an age range, or removing certain attributes entirely. Tokenization, replacing sensitive data with a non-sensitive equivalent, a token, that can be mapped back to the original data in a secure system, unlike a hash. Differential privacy, adding controlled noise to data queries or outputs to prevent individual re-identification while preserving overall statistical properties. For many GNN projects, especially those dealing with user interactions or profiles, applying hashing to unique identifiers, like user IDs or emails, at the raw data stage is a foundational and highly recommended first step in ensuring data privacy. Subsequent steps in the pipeline will then operate on these pseudonymized identifiers. Raw data, the starting point for graph neural networks. Raw data serves as the fundamental input for any graph neural network, GNN, project. It represents the initial, unprocessed information collected from various sources, existing in its most basic form before any transformations or structuring specifically for graph analysis. Understanding raw data is crucial because its characteristics directly influence subsequent steps in the GNN pipeline, from data modeling to encoding and feature engineering. In the context of GNNs, Raw data often originates from diverse real-world sources, including log files, capturing interactions, e.g., user clicks, network traffic, system events that can form temporal graphs. Relational databases, tables containing entities and their relationships, which can be extracted and converted into nodes and edges. Text documents, requiring natural language processing, NLP, to extract entities, nodes, and their semantic relationships, edges. Sensor readings, time series data from IoT devices, where sensors can be nodes and their co-occurrence or spatial proximity can define edges. Social media feeds, user profiles as nodes and friendships, likes or mentions as edges. While raw data is the starting point, it is rarely in a format directly usable by GNN frameworks. It often suffers from several real-world challenges. Data cleanliness, containing errors, duplicates, or irrelevant entries. Missing values, incomplete records that could disrupt GRA. pH construction, inconsistencies, variations in data entry or format across different sources. Schema drift, changes in the data structure over time, which can break predefined parsing logic. Addressing these issues early in the pipeline, even before full preprocessing, is vital. Initial validation checks, such as ensuring unique identifiers or expected data types, can prevent downstream failures. Data encoding and serialization, bridging systems. Once raw data is identified, a critical step is to prepare it for transfer and consumption by different components of the GNN pipeline. This involves data encoding and data serialization. While these terms are often used interchangeably in practice, it's helpful to understand their subtle distinction. Serialization is the process of translating data structures or object states into a format that can be stored, e.g., on disk, or transmitted, e.g., over a network, and reconstructed later. Encoding refers to the specific scheme or format used during serialization to represent the data. For instance, JSON, CSV, or XML are common encoding formats for serialized data. In GNN projects, encoding and serialization are crucial for interoperability, enabling data exchange between different programming languages, operating systems, and software components, e.g., a Python script generating graph data, a Java application consuming it, and a C++ GNN framework processing it. Persistence, storing processed graph data efficiently for LAT, or use or analysis. Efficient transfer, optimizing the size and structure of data for faster network transmission or disk I/O. Representing graph data in raw formats. Before delving into specific encoding formats, it's essential to understand how fundamental graph structures, adjacency lists, edge lists, and adjacency matrices, are conceptualized and typically represented in raw data. The choice of representation often dictates the most suitable encoding format. Adjacency lists. An adjacency list represents a graph as a mapping where each node is associated with a list of its neighboring nodes. This is particularly efficient for sparse graphs, graphs with relatively few edges compared to the number of possible edges, as it only stores existing connections. Consider a small social network where individuals refer others. The raw data might look like a mapping from a recommending candidate to a list of recommended candidates. For privacy, candidate IDs might be hashed. Code is not spoken. To get code, please see the link in description or bio. Here's a concrete example of raw data representing referral logs in an adjacency list-like structure using JSON. It demonstrates how candidate IDs, hashed for privacy, are mapped to lists of other candidate IDs they have referred or are connected to. Code is not spoken. To get code, please see the link in description or bio. This JSON structure implicitly represents an adjacency list. The code snippet object maps a source node's hash to an array of its neighbors' hashes. The code snippet provides a simple lookup for understanding the example, though in a real scenario, this mapping might be stored separately or not at all if only hashes are needed. To practically use this raw JSON data in a Python environment, you would typically load it into a Python dictionary. Code is not spoken. To get code, please see the link in description or bio. This snippet demonstrates how easily JSON data can be parsed into a native Python dictionary, making it accessible for further processing. Edge lists. An edge list is perhaps the simplest way to represent a graph, consisting of a collection of tuples, where each tuple represents an edge connection between two nodes. It can optionally include an edge weight or type. This format is highly intuitive and easy to parse, especially for tabular data. Consider the same social network referral example. An edge list would explicitly list each referral as a pair of refer, referred. Code is not spoken. To get code, please see the link in description or bio. This CSV format clearly lays out each relationship as a row. The first column is the source, the second is the target, and an optional third column describes the relationship. Loading and parsing this CSV data into a list of tuples or a pandas data frame in Python is straightforward. Code is not spoken. To get code, please see the link in description or bio. This example shows how code snippet can efficiently load CSV data, which is then easily convertible to a list of tuples, a common format for many graph libraries. Adjacency matrices. An adjacency matrix represents a graph as a square matrix where rows and columns correspond to nodes. A cell code snippet contains a code snippet or a weight if there is an edge from node code snippet to node code snippet and code snippet otherwise. For a small graph with nodes Alice, Bob, Charlie, David, we first need to map them to integer indices, e.g., Alice equals 0, Bob equals 1, Charlie equals 2, David equals 3. Code is not spoken. To get code, please see the link in description or bio. The output shows a 4 by 4 matrix where code snippet indicates an edge. For instance, code snippet is code snippet because Alice, 0, refers Bob, 1. Code is not spoken. To get code, please see the link in description or bio. Dense versus sparse matrices. Dense matrices are suitable for small graphs or graphs where most nodes are connected, dense graphs. However, for large real-world graphs, which are typically sparse, a dense matrix can consume an enormous amount of memory because it stores zeros for non-existent connections. Sparse matrices only store the non-zero elements, making them highly memory efficient for sparse graphs. Libraries like SciPy provide optimized sparse matrix formats, e.g., CSR, compressed sparse row, so coordinate format. Conceptually, a sparse matrix for the above example would store only the location's code snippet and values code snippet for each EDG, rather than the full code snippet grid. Code is not spoken. To get code, please see the link in description or bio. The code snippet object provides an efficient internal representation. When converted to code snippet, it reconstructs the same dense matrix for verification. Code is not spoken. To get code, please see the link in description or bio. Common encoding formats in detail. The choice of encoding format depends on various factors, including the complexity of the data, the systems involved, and performance requirements. JSON, JavaScript Object Notation. JSON is a lightweight, human-readable data interchange format. Its structure, based on key value pairs and ordered lists, makes it highly flexible for representing complex, nested data, including graph data structures like adjacency lists or node/edge attributes. Pros: human-readable, easy to inspect and debug, widely supported, native parsers in almost all modern programming languages and web browsers. Flexible schema, no strict predefined schema, allowing for varied data structures within the same file. Cons: verbose, can be larger than binary formats for the same data, leading to higher storage and transfer costs. Less efficient for very large graphs. Parsing large JSON files can be slower compared to optimized binary formats. Use cases: APIs exchanging graph data. Configuration files for GNN models. Storing small to medium-sized graph datasets, especially those with rich node/edge attributes. CSV, comma-separated values. CSV is a simple, tabular data format where values are separated by commas. It's excellent for representing flat tables, making it a natural fit for edge lists or lists of node attributes. Pros: simplicity and universality. Can be opened and edited with any text editor or spreadsheet software. Compact for tabular data. Relatively efficient for simple, flat structures. Cons: no inherent schema. Requires external knowledge of column meanings and data types. Limited flexibility. Poorly suited for nested or hierarchical data, like adjacency lists. Ambiguity. Commas within data values need careful handling, e.g., quoting. Use cases. Storing edge lists, code snippet. Storing node or edge attribute tables, code snippet. When interoperability with non-technical users or spreadsheet tools is required. XML, extensible markup language. XML is a markup language designed to store and transport data. It allows for arbitrary tags and nested structures, making it highly expressive and capable of representing complex hierarchies. Pros: self-describing. Tags provide context to the data. Highly structured. Supports strict schema validation, e.g., XML schema definition, XSD, ensuring data consistency. Cons: very verbose. Significantly larger than JSON or CSV for equivalent data, leading to higher overhead. Parsing overhead. More complex to parse programmatically. Declining use. Less common for new data interchange projects compared to JSON, though still prevalent in legacy systems. Use cases. Document-centric data. Integration with older enterprise systems. Some graph visualization tools, e.g., GraphML, a common XML-based format for graphs. Language-specific formats, e.g., Python Pickle. Many programming languages offer their own serialization mechanisms to convert in-memory objects directly into a byte stream. For Python, this is typically done using the code snippet module. Pros: preserves object structure. Can serialize complex Python objects, e.g., custom classes, network-X graph objects, directly, including their methods and attributes. Efficient for language-specific transfer. Fast for Python to Python data exchange. Cons: not interoperable. Pickled data cannot be easily deserialized by programs written in other languages. Security risks. Deserializing data from an untrusted source can execute arbitrary code, posing a significant security vulnerability. Use cases. Caching intermediate results within a Python-only pipeline. Saving and loading trained GNN models, though more secure formats like PyTorch's code snippet are preferred for models. Internal pipeline stages where data doesn't need to leave the Python ecosystem. Binary/optimized formats, e.g., Apache Parquet, Avro, protocol buffers. These formats are designed for high performance and efficiency, often sacrificing human readability for compactness and speed. They typically require specific libraries for serialization and deserialization. Pros: compact, significantly smaller file sizes than text-based formats. Efficient, faster reading and writing, especially for large datasets. Schema evolution. Many support changes to the schema over time without breaking compatibility. Cross-language. Protocol buffers and Avro are designed for cross-language interoperability. Cons: not human-readable. Requires specialized tools to inspect the data. Requires specific libraries. Cannot be easily opened or edited without the right software. Use cases. Large-scale data lakes and data warehousing, Parquet, Avro. High-performance data pipelines where speed and storage efficiency are paramount. Microservices communication, protocol buffers, Thrift. Storing very large graph datasets or dense feature matrices. Key considerations for choosing an encoding format. Selecting the appropriate encoding format for your raw graph data is a critical decision that impacts the entire GNN pipeline. Several factors should guide this choice. Data model and schema. The inherent structure and complexity of your graph data play a significant role. Data model. How do your nodes, edges, and their associated attributes naturally fit into a structured format? For example, if you have deeply nested attributes for nodes, JSON, or XML might be more suitable than CSV. Schema. Do you need a strict, enforced schema for data validation and consistency, or can the schema be more flexible? Formats like Avro or protocol buffers enforce. Schemas. While JSON is more flexible and CSV has no inherent schema. Defining a clear schema, even if not strictly enforced by the format, is a best practice for data quality. Data structure. The specific graph representation, adjacency list, edge list, or matrix you choose or receive as raw input heavily influences the best encoding format. Adjacency lists, best suited for formats that support nested structures, such as JSON or XML. Edge lists, ideal for tabular formats like CSV, Parquet, or Avro. Adjacency matrices, often stored as specialized sparse matrix formats, e.g., SIPY's code snippet for number py/scipy arrays, or within binary formats optimized for numerical data. The choice of data structure directly impacts the storage size and transfer efficiency. A sparse graph represented as a dense matrix in JSON will be much larger than the same graph as an edge list in CSV or a sparse matrix in a binary format. Receiving systems and interoperability. Consider all the downstream systems that will consume this raw data. Compatibility. Does the chosen format seamlessly integrate with your graph databases, GNN libraries, e.g., PyTorch geometric, DGL, analytics tools, or other programming languages? Cross-system data exchange. If data needs to be transferred between different software components or even different organizations, widely adopted and language-agnostic formats like JSON or CSV are generally preferred over language-specific ones like Pickle. System-driven for. MOTS. Sometimes, the choice of format is dictated by an external system. For example, a specific graph database might export data in its own proprietary binary format, or a legacy system might only produce XML. Advantages. These formats are often highly optimized for operations within that specific system, ensuring efficient data exchange with it. Disadvantages. They can lead to vendor lock-in and require custom parsing logic if you need to integrate with other systems. Efficiency, storage, transfer, and processing. The scale of your data and the performance requirements of your pipeline are crucial. Storage size. For very large data sets, compact binary formats will significantly reduce storage costs. Transfer speed. Smaller file sizes translate to faster network transfer times. Processing efficiency. The time taken to parse and load the data into memory can be a bottleneck. Binary formats are generally faster to parse than text-based ones. Sparse versus dense. For sparse graphs, using a sparse matrix representation in an optimized binary format is vastly more efficient in terms of both storage and processing than a dense matrix representation, especially as the number of nodes grows. Common pitfalls and best practices in raw data handling. Effectively managing raw data is foundational for successful GNN projects. Ignoring common pitfalls can lead to significant issues downstream. Data cleanliness and validation. Pitfall. Assuming raw data is clean and immediately use app. Real-world data is almost always messy. Best practice. Implement initial data validation checks immediately upon ingestion. This includes missing values. Identify and decide on a strategy, imputation, removal. Inconsistencies. Standardize data formats, e.g., date formats, string casing. Malformed records. Filter out or flag data that doesn't conform to expected structures. Referential integrity. For graph data, ensure that all referenced nodes actually exist. Schema drift. Pitfall. Inflexible parsing logic that breaks when the raw data schema changes. Best practice. Design data ingestion pipelines to be resilient to schema changes. This might involve schema versioning. Clearly define and track different versions of your raw data schema. Flexible parsers. Use parsers that can handle missing fields or new fields gracefully, e.g., by providing default values or ignoring unknown fields. Monitoring. Set up alerts for schema mismatches. Data privacy and security. Pitfall: handling sensitive raw data, like personally identifiable information, PII, without proper precautions. Best practice: anonymization/hashing. As seen in the example, hash or anonymize sensitive identifiers as early as possible in the pipeline. Access controls. Implement strict access controls to raw data storage. Encryption. Encrypt data at rest and in transit. Choosing the right tool for the job. Pitfall: over-engineering or under-engineering the data format choice. Best practice: IGN the format choice with project scale and requirements. Small research prototype. A simple JSON or CSV might suffice for rapid iteration. Large-scale production system. Binary formats like Parquet or Avro, combined with sparse matrix representations, will be essential for performance and cost efficiency. Hypothetical scenario. Imagine building a GNN to detect fraud in a financial transaction network. If you choose to store billions of transactions as a dense adjacency matrix in a JSON file, you'd quickly run out of memory and storage, and parsing would be prohibitively slow. An edge list in a compressed binary format, e.g., Parquet, and processed as a sparse graph would be the appropriate choice, balancing storage, transfer, and processing needs. By carefully considering these aspects of raw data, from its initial form and representation to its encoding and common challenges, you lay a solid foundation for a robust and efficient GNN pipeline. The ETL step. The extract, transform, load, ETL step is a foundational process in any data pipeline, and it is particularly critical when preparing raw, non-graph data for graph neural network, GNN, projects. This stage acts as the bridge between your initial raw data sources and the structured graph format required by GNNs. It ensures that the data is not only clean and consistent, but also conforms to the predefined graph schema. The primary goal of ETL in a GNN context is to convert disparate, often non-graph native data, like JSON documents, relational database tables, or CSV files, into a structured representation of nodes, entities, and edges relationships, along with their respective features. 1. Extract, gathering raw data. The extract phase involves reading data from its original source. This source can vary widely, from structured databases, SQL, NoSQL, to semi-structured files, JSON, XML, or even unstructured text documents. For GNNs, the raw data often describes entities and their interactions, which implicitly contain graph structures. Consider a scenario where we have raw data about job candidates and the jobs they've applied for, stored in a JSON format. This data might look like a collection of candidate profiles, each containing information about the candidate and a list of their applications. Code is not spoken. To get code, please see the link in description or bio. Sample raw JSON data representing candidates, their applications, and job details. To begin the ETL process, we first need to read this raw JSON data into our programming environment. Python's code snippet library is well suited for this task. Code is not spoken. To get code, please see the link in description or bio. This initial code block sets up a dummy JSON file for demonstration purposes and then provides a robust function to read it. The code snippet function includes basic error handling for code snippet and code snippet, which are common pitfalls during the extraction phase. 2. Transform, shaping data into graph structures. The transform phase is the most complex and crucial part of the ETL process for GNNs. This is where raw, disparate data is converted into explicit graph components, nodes, edges, and their associated features. This transformation must strictly adhere to the predefined graph schema, discussed in earlier sections, ensuring that the resulting graph is semantically meaningful and suitable for GNNs. For our application data, we need to identify nodes, candidates, and jobs. Edges, applied for relationships between candidates and jobs. Node features, attributes of candidates, e.g., code snippet, and jobs, e.g., code snippet, code snippet. Edge features, optional attributes of the application, e.g., code snippet. The transformation process involves iterating through the raw data and programmatically constructing lists of nodes and edges. A common and highly flexible intermediate format for graph data is the edge list A. ND separate node feature lists. An edge list is simply a collection of tuples, where each tuple represents an edge code snippet. Let's break down the transformation logic. Identifying nodes and edges. First, we'll process the raw data to identify all unique candidates and jobs, our nodes, and then derive the applied for relationships, our edges. We also want to gather initial node features from the raw data. Code is not spoken. To get code, please see the link in description or bio. This function code snippet iterates through the raw JSON data. It intelligently distinguishes between candidate and job entries to populate a code snippet dictionary, mapping node IDs to their attributes, and an code snippet list, representing relationships. It also includes a basic validation step to identify and handle potential issues where an edge might reference a node for which no features were explicitly defined in the raw data, preventing common errors downstream. Adjacency list representation, conceptual. While we are primarily generating an edge list, it's useful to understand how an adjacency list relates. An adjacency list represents a graph as a mapping from each node to a list of its neighbors. For instance, code snippet. Graph libraries like NetworkX or PyTorch Geometric often convert edge lists into adjacency lists internally for efficient graph traversal. The transformation to an adjacency list usually happens after the initial ETL, often during graph loading, as it's a specific data structure for graph processing rather than a generic serialization format. Handling data inconsistencies and errors. During the transformation, real-world data often presents challenges. Missing values. An application might lack a code snippet. Our code currently skips such malformed entries. A more robust approach might log these, assign default values, or flag them for manual review. Malformed data. Non-numeric IDs where numbers are expected, incorrect date formats, etc. Duplicates. Duplicate candidate or job entries. Our current approach uses dictionaries for code snippet, which inherently handles duplicate keys by overriding, effectively keeping only the last encountered feature set for a given ID. For edges, code snippet can be used to remove exact duplicates if needed. Schema mismatches. Data fields not matching the expected graph schema. Best practice dictates implementing explicit validation and error handling. Validation rules. Define expected data types, ranges, and formats for each field. Error logging. Log records that fail validation, rather than silently skipping them. Data cleaning. Implement strategies to impute missing values or normalize formats. Fallback values. Provide default values for optional fields if they are missing. For simplicity, our example uses basic code snippet and conditional checks, which provide a degree of fault tolerance by gracefully handling missing keys. Code is not spoken. To get code, please see the link in description or bio. The code snippet function uses the code snippet library to convert our lists of dictionaries into data frames, which are then easily written to CSV files. The code snippet argument prevents pandas from writing the data frame index as a column in the CSV. For node features, careful restructuring is performed to ensure code snippet and code snippet are prominent columns, making the output clear and usable. Example output CSVs. Code snippet. Code is not spoken. To get code, please see the link in description or bio. Code snippet. Code is not spoken. To get code, please see the link in description or bio. Notice how the code snippet list is serialized as a string within the CSV. While this is acceptable for basic storage, when loading into GNN libraries, these features might need further parsing, e.g., converting back to a list or one-hot encoding categorical values. 3. Load. Preparing for graph processing. The load phase involves writing the transformed data into a format that can be easily consumed by downstream systems, such as graph processing libraries, e.g., NetworkX, iGraph, or GNN frameworks, e.g., PyTorch Geometric, PYG, DGL. CSV files are a common and highly portable choice for this intermediate serialization due to their simplicity and wide support. The final step in the EDL process is to ensure the data is ready for ingestion by graph libraries. This often means reading the CSV files we just created and constructing a graph object in Memo. Edit. Code is not spoken. To get code, please see the link in description or bio. This final code block demonstrates how the generated CSVs would be read and used to construct a graph. It shows explicit ingestion into code snippet, a popular general-purpose graph library, which is useful for exploratory data analysis, visualization, and basic graph algorithms. It also conceptually outlines how the data would be prepared for a GNN library like PyTorch Geometric, emphasizing the need for numerical indexing and feature tensor creation, which are often part of a subsequent pre-processing step rather than the core EDL. Computational complexity and best practices. For small datasets, the described ETL process is efficient enough. However, for larger datasets, millions of nodes/edges, several considerations become important. Memory usage. Loading entire datasets into memory, code snippet, or large lists can become prohibitive. Solutions include streaming/chunking, process data in smaller batches. Specialized libraries. Use libraries designed for large-scale data processing, e.g., Dask, Apache Spark. Performance. Iterating through millions of records in Python can be slow. Vectorization. Utilize code snippet or NumPy's vectorized operations instead of explicit loops where possible. Optimize data stores. For very large graphs, consider dedicated graph databases, e.g., Neo4j, ArangoDB, or graph file formats, e.g., Parquet, Feather, that are optimized for read/write performance. Modularity. Break down the ETL process into distinct, testable functions, e.g., code snippet, code snippet, code snippet. This improves maintainability and debugging. Error handling. Implement robust error handling and logging to identify and address data quality issues early. Idempotence. Design EDL scripts to be idempotent, meaning running them multiple times produces the same result, which is crucial for reproducibility and recovery from failures. Version control. Keep EDL scripts under version control, as changes to data sources or schema will require updates to the transformation logic. The ETL step is a critical and often iterative process. It requires a deep understanding of both the raw data structure and the target graph schema. By carefully designing and implementing the extract, transform, and load phases, you lay a solid foundation for successful GNN model development. The ETL step. Raw data to adjacency list and edge list. The extract, transform, load, EDL process is fundamental to preparing any data for analytical or computational tasks, and graph neural networks, GNNs, are no exception. While the extract phase focuses on retrieving raw data and load on storing the processed data, the transform phase is where the magic happens, converting raw, often non-graph structured information into the precise graph representations required by GNNs. This section delves into the practical implementation of transforming raw JSON data into two foundational graph data structures, the edge list and the adjacency list. Understanding core graph representations. Before diving into the transformation, it's crucial to solidify our understanding of the target graph representations. Edge lists. An edge list is arguably the simplest way to represent a graph. It is a collection of tuples, where each tuple code snippet denotes a connection, an edge, from node code snippet to node code snippet. Structure. Typically a list of two-element tuples code snippet. Pros. Simplicity. Easy to understand and implement. Memory efficiency for sparse graphs. For graphs with relatively few edges compared to the number of possible edges, sparse graphs, an edge list can be very memory efficient as it only stores existing connections. Direct input from many libraries. Many graph processing libraries, including GNN frameworks like PyTorch Geometric, can directly ingest D. ADA in an edge list format. Cons. Inefficient for neighbor lookups. Finding all neighbors of a specific node requires iterating through the entire list, which can be slow for large graphs. OE complexity, where E is the number of edges. Difficulty in detecting isolated nodes. Nodes with no connections, isolated nodes, are not explicitly present in an edge list. Adjacency lists. An adjacency list represents a graph as a mapping where each node is associated with a list of its direct neighbors. This structure is particularly efficient for operations that involve traversing the graph by exploring neighbors. Structure. Typically a dictionary or hash map where keys are nodes and values are lists or sets of their adjacent nodes. For example, code snippet. Pros. Efficient neighbor lookups. Finding all neighbors of a node is very fast. Degree node. Complexity. Easy to add, remove edges. Modifying connections is straightforward. Explicit node representation. All nodes, including isolated ones, can be explicitly represented. Cons. Higher memory usage for dense graphs. For graphs where nodes have many connections, dense graphs, storing all neighbor lists can consume more memory than an edge list, though this is often negligible for typical GNN datasets. Less direct for some GNN inputs. While highly useful for general graph algorithms, GNN libraries often prefer edge lists or adjacency matrices for their input formats. However, it's easy to convert an adjacency list to an edge list, choosing the right representation. The choice between an edge list and an adjacency list often depends on the primary operations you intend to perform. If your main goal is to feed data into a GNN, an edge list is often a direct path. If you need to frequently query a node's neighbors or perform graph traversal algorithms, like breadth-first search or depth-first search, before GNN processing, an adjacency list is superior. Fortunately, converting between these two formats is straightforward once the raw data is structured. Extracting raw data, loading JSON. Our raw data often comes in semi-structured formats like JSON. For this example, we'll consider a JSON file where keys represent recommending users and values are lists of recommended users. This structure inherently describes directed relationships. Let's assume our raw data is stored in a file named code snippet with the following content. Code is not spoken. To get code, please see the link in description or bio. In this JSON, code snippet recommends code snippet and code snippet. Code snippet recommends code snippet and code snippet, and so on. Notice that code snippet is a user who is recommended by code snippet, but recommends no one herself, illustrating a potential isolated node from a recommending perspective. The first step in our transformation process is to load this JSON data into a Python dictionary. The built-in code snippet module is perfectly suited for this. Code is not spoken. To get code, please see the link in description or bio. This code snippet first ensures our dummy code snippet file exists for reproducibility. Then, it attempts to open and load the JSON file using code snippet. The code snippet block is a best practice for file operations, gracefully handling cases where the file might not exist, code snippet, or if the JSON content is malformed, code snippet. After successful loading, code snippet will hold the entire JSON content as a standard Python dictionary. Transforming data from JSON to edge list. Our code snippet now holds the direct recommendations. To convert this into an edge list, we need to iterate through each key value pair. Each key represents a source node, and each item in its corresponding value list represents a target node. This directly translates to a directed edge code snippet. Algorithmic logic for directed edges. 1. Initialize an empty list to store the edges. 2. Iterate through each code snippet key and its code snippet value list in code snippet. 3. For each code snippet in code snippet, create a tuple code snippet and add it to our edge list. Code is not spoken. To get code, please see the link in description or bio. The code snippet will now contain tuples representing the recommends relationships as they appear in the raw JSON. For our example, it would look like code snippet. Handling undirekte graphs. In many GNN applications, relationships are considered undirected, e.g., friendships, cout. Horseship, if our recommendation graph is meant to be undirected, meaning if Alice recommends Bob, then Bob also implicitly recommends Alice. We need to add reciprocal edges. Algorithmic logic for undirected edges. 1. Start with the code snippet. 2. Use a code snippet to store edges to automatically handle duplicates and ensure uniqueness when adding reciprocal edges. 3. For each code snippet edge in the directed list, add both code snippet and code snippet to the set. 4. Convert the set back to a list. Code is not spoken. To get code, please see the link in description or bio. The code snippet will now contain both code snippet and code snippet for every connection, unless code snippet and code snippet are the same node, a self loop. This is crucial for libraries that expect explicit representation of both directions for undirected graphs. For our example, it will contain code snippet, code snippet, code snippet, code snippet, etc. Transforming data from JSON to adjacency list. Converting the raw JSON data into an adjacency list involves a similar iteration process. But instead of creating tuples for edges, we build a dictionary where each key maps to a list of its neighbors. Algorithmic logic for directed adjacency list. 1. Initialize an empty dictionary for the adjacency list. 2. Iterate through each code snippet key and its code snippet value list in code snippet. 3. For each code snippet, ensure it exists as a key in the adjacency list dictionary. If it doesn't, initialize its value to an empty list. 4. Extend or append the code snippet to the code snippets list of neighbors. 5. Also, ensure all code snippets from the code snippet are present as keys in the adjacency list, even if they don't recommend anyone, to represent all nodes in the graph. Code is not spoken. To get code, please see the link in description or bio. The code snippet will represent the recommends relationships. For our example, code snippet, code snippet, code snippet, code snippet, code snippet. Note, Eve is now explicitly a node in the graph, even if she has no outgoing edges. Handling undirected graphs with adjacency lists. For an undirected graph, if code snippet is connected to code snippet, then code snippet is also connected to code snippet. This means we need to ensure symmetry in our adjacency list. If code snippet is in code snippet's neighbor list, then code snippet must be in code snippet's neighbor list. Algorithmic logic for undirected adjacency list. 1. Start with a code snippet or build from scratch. For simplicity, we'll build from scratch, ensuring symmetry. 2. Initialize an empty dictionary for the undirected adjacency list. 3. Iterate through each code snippet and its code snippet in code snippet. 4. For each code snippet and code snippet pair, add code snippet to code snippet's neighbor list. Add code snippet to code snippet's neighbor list. Use code snippets for neighbor lists temporarily to avoid duplicate entries for the same node. 5. After processing all initial recommendations, iterate through all nodes that have appeared, either as source or target, and ensure they are keys in the adjacency list, initializing with empty sets if necessary. Convert sets to lists at the end. Code is not spoken. To get code, please see the link in description or bio. The code snippet will now reflect the symmetric relationships. For our example, code snippet, code snippet, code snippet, code snippet, code snippet. Notice how code snippet now recommends code snippet, because code snippet recommends code snippet, and code snippet recommends code snippet, and code snippet recommends code snippet, and code snippet recommends code snippet. Wait, this is simply adding reciprocal edges. If A recommends B, then B is added to A's list, and A is added to B's list. So, code snippet is in code snippet's list, and code snippet is in code snippet's list. Code snippet is in code snippet's list, and code snippet is in code snippet's list. Code snippet is in code snippet's list, and code snippet is in code snippet's list. Code snippet is in code snippet's list, and code snippet is in code snippet's list. This is correct for the logic applied. Practical considerations and best practices. Handling missing data. Our example assumes clean data. In real-world scenarios, code snippet might be code snippet or missing. Robust code would include checks, e.g., code snippet. Data validation. Before transformation, consider validating your raw data. A. Renode names consistent? Are there self-loops, a node recommending itself, that you might want to filter out? Scalability. For very large data sets that don't fit into memory, consider processing data in chunks or using specialized libraries for graph processing, like NetworkX, that handle large graphs more efficiently, or even graph databases, Neo4j, Amazon Neptune, for persistence and complex queries. Node attributes. Our current transformation only deals with connections. Real-world GNNs often require node features attributes. The ETL process would extend to extract these attributes and associate them with the corresponding nodes, typically stored in a separate node feature matrix. Edge attributes. Similarly, edges can have attributes, e.g., strength of recommendation, timestamp. These would also be extracted and stored alongside the edge list or adjacency list. Downstream use. The generated edge lists and adjacency lists are now in a format readily consumable by many graph libraries. For instance, NetworkX can directly build a graph from an edge list using code snippet or code snippet. PyTorch geometric expects in code snippet tensor, a 2xn tensor where n is the number of edges, which is easily derived from our edge list. By meticulously transforming raw, semi-structured data into these fundamental graph representations, we lay the groundwork for effective graph analysis and a successful application of graph neural networks. This transform step is not mere a technical conversion, but a critical conceptual bridge from raw information to structured knowledge, ready for the sophisticated algorithms that follow. Creating an adjacency list. The transform phase of the ETL extract, transform, load, pipeline is where raw, often unstructured, data is converted into a format suitable for the next stages of processing. For graph neural networks, GNNs, this typically means transforming relational data into a graph representation, such as an adjacency list or an edge list. This section focuses on the practical implementation of creating an adjacency list from raw relationship data, with a critical emphasis on ensuring graph symmetry for undirected graphs. Understanding adjacency lists. An adjacency list is a collection of unordered lists used to represent a finite graph. Each list describes the set of neighbors of a vertex in a graph. For a node code snippet, its adjacency list would contain all nodes code snippet that code snippet is connected to. This representation is highly efficient for sparse graphs with relatively few edges, because it only stores existing connections. Consider a simple social network where individuals refer others. Our raw data might look like a dictionary where keys are refer IDs and values are lists of referred IDs. Code is not spoken. To get code, please see the link in description or bio. In an adjacency list, we want to represent all connections. If code snippet refers code snippet is adjacent to code snippet. If code snippet refers code snippet, then code snippet is adjacent to code snippet. Ensuring graph symmetry for undirected graphs. Many real-world graphs, especially in GNN applications, are undirected. This means that if node code snippet is connected to node code snippet, then node code snippet is also connected to node code snippet. In the context of an adjacency list, if code snippet appears in code snippet's adjacency list, then code snippet must appear in code snippet's adjacency list. The raw data format often captures directed relationships, e.g., code snippet refers code snippet is a directed edge from code snippet to code snippet. To convert this into an undirected graph representation, we must explicitly add the reverse relationship. For example, if code snippet refers code snippet, we must also record that code snippet is referred by code snippet, or, more generally, that code snippet is adjacent to code snippet. Let's trace this with a small example. Suppose our raw data is code snippet. If this represents an undirected graph, Then code snippet is connected to code snippet, and code snippet is connected to code snippet. Our adjacency list should reflect this. Code snippet. Code snippet. The transformation process must ensure that when code snippet is added to code snippets list, code snippet is also added to code snippets list. This is a crucial step to correctly model undirected relationships from potentially directed raw data. Implementing the adjacency list transformation. We will now build a Python function, code snippet, that performs this transformation. The function will take the raw data dictionary as input, ensure symmetry, and then write the resulting adjacency list to a text file. Function initialization and node tracking. The function starts by defining the function signature and initializing an empty list to keep track of all unique nodes encountered in the graph. This list of nodes can be useful for subsequent processing steps, such as mapping node names to integer indices. Code is not spoken. To get code, please see the link in description or bio. The code snippet will accumulate all unique node IDs, both source and target, as we process the relationships. This is important because a node might only appear as a target in the input data, but still needs to be recognized as part of the graph. Processing relationships and ensuring symmetry. This is the core logic where we iterate through the input relationships and modify the code snippet in place to ensure symmetry. Code is not spoken. To get code, please see the link in description or bio. In this section, we iterate through each code snippet and its code snippets. For each code snippet, we perform the crucial symmetry check. 1. If code snippet is not yet a key in code snippet, this means code snippet hasn't been recorded as referring to anyone. We create a new entry for it in code snippet and add code snippet to its list. 2. If code snippet is already a key, we check if code snippet is already in code snippets list. If not, we append code snippet to ensure the reverse relationship is captured. This process modifies the code snippet in place. This design choice means the original code snippet pass to the function will be altered. While efficient for memory, it's important to be aware of this side effect, as the caller's data will be changed. If the original code snippet needs to be preserved, a copy should be made before passing it to the function, e.g., code snippet. Let's trace the in-place modification with an example. Initial code snippet. Code snippet. 1. Code snippet, code snippet. Code snippet and code snippet added to code snippet. Code snippet is a key. Is code snippet in code snippet? No. Code snippet dash, code snippet becomes code snippet. 2. Code snippet, code snippet. Code snippet added to code snippet. Code snippet is not a key. Code snippet dash, code snippet becomes code snippet. Final code snippet after symmetry enforcement. Code snippet. This symmetrical dictionary is now ready for output. Alternative. Using code snippet for cleaner symmetry logic. The in-place modification logic, while functional, can be made more concise and Pythonic using code snippet. A code snippet automatically creates a default value for a key if it's not found when accessed. Code is not spoken. To get code, please see the link in description or bio. Using code snippet means that code snippet will automatically initialize as an empty list if code snippet is accessed for the first time, eliminating the need F. Or code snippet checks. This leads to cleaner and often less error-prone code for building dynamic dictionaries. For the rest of this section, we will continue with the original in-place modification approach as detailed in the professor's analysis. But code snippet is a valuable alternative for future implementations. Writing the adjacency list to a file. Once the code snippet has been made symmetrical, the next step is to persist this information to a file. A plain text file, code snippet, is a straightforward choice for this. Code is not spoken. To get code, please see the link in description or bio. Here's a breakdown of the file writing process. File name construction. The code snippet is dynamically created, optionally including a code snippet for better organization, e.g., code snippet. File opening mode, code snippet this mode, is crucial. It ensures that if the file already exists, it's cleared before new content is written, preventing old data from mixing with new. If the file doesn't exist, it's created. iteration, and formatting. The code iterates through the keys of the code snippet, which now contains all symmetrical relationships. For each code snippet, its list of code snippets is joined into a single space-separated string using code snippet. Sorting the keys and their respective target lists, code snippet and code snippet, ensures that the output file is consistently ordered, which aids in debugging and comparison. Line termination. Each line is termy. Nate with code snippet, new line character, to ensure proper line breaks in the text file. Error handling. Code snippet basic error handling is included using a code snippet block to catch potential code snippet exceptions during file operations, e.g., permission issues, disk full. This makes the function more robust. Code snippet. Using code snippet is a best practice in Python for file handling. It ensures that the file is automatically closed, even if errors occur, preventing resource leaks. Returning all unique nodes. Finally, the function returns the code snippet that was populated throughout the process. Code is not spoken. To get code, please see the link in description or bio. The return code snippet provides a comprehensive list of all participants in a graph. This is often a necessary input for graph processing frameworks where nodes need to be assigned unique integer IDs or for verifying that all expected nodes are present. Complete adjacency list creation function. Combining all the pieces, here is the complete code snippet function. Code is not spoken. To get code, please see the link in description or bio. Example usage and output verification. Let's demonstrate how to use this function with a sample dataset and verify its output. Code is not spoken. To get code, please see the link in description or bio. After running the code, a file named code snippet will be created in the same directory. Its content will look like this. Code is not spoken. To get code, please see the link in description or bio. Let's visualize this small graph for clarity. Code is not spoken. To get code, please see the link in description or bio. The output file shows that code snippet is connected to code snippet, and code snippet. Code snippet is connected to code snippet, and code snippet. Code snippet is connected to code snippet and code snippet. Code snippet is connected to code snippet. Code snippet is connected to code snippet. This correctly reflects the symmetrical relationships derived from the raw data. Helper function to read back adjacency list. To further verify the output, we can create a simple helper function to read the generated code snippet file back into a Python dictionary. Code is not spoken. To get code, please see the link in description or bio. This code snippet function parses each line, splitting it by space to reconstruct the node and its neighbors. This allows for programmatic verification of the generated file's content. Creating an edge list. While an adjacency list is useful, an edge list is another common and often simpler graph representation, especially for input into GNN libraries. An edge list is simply a collection of pairs or triplets if edges have attributes, representing connections between nodes. From our transform code snippet, we can easily generate an edge list. Code is not spoken. To get code, please see the link in description or bio. The code snip. T function iterates through the symmetrical adjacency list. It uses a code snippet set to ensure that each undirected edge is recorded only once. E.g., if code snippet is added, code snippet is not added as a separate edge. The output file code snippet would look like this. Code is not spoken. To get code, please see the link in description or bio. Performance considerations. For very large graphs, the repeated use of code snippet and code snippet checks on code snippet, which is a list, can become inefficient, as code snippet checks on lists have code snippet complexity. For extremely large datasets, using a code snippet for code snippet to track unique nodes, code snippet, would improve the lookup time to code snippet on average. Similarly, when building the adjacency lists themselves, code snippet as discussed, or more specialized graph libraries like NetworkX, can offer better performance and more robust feature for large-scale graph manipulation. Conclusion. Transforming raw data into a structured graph representation like an adjacency list, is a fundamental step in any GNN pipeline. This section has demonstrated how to implement this transformation in Python, focusing on the critical aspect of ensuring graph symmetry for undirected graphs. By understanding the in-place modification of data structures, the nuances of file I/O, and the utility of different graph representations, you are well equipped to prepare diverse datasets for graph-based machine learning tasks. Creating an edge list. The previous sections discussed the initial steps of the extract, transform, load, ETL process for graph neural networks, GNNs, including defining graph representations and creating an adjacency list. This section shifts focus to another fundamental graph representation, the edge list. We will explore its structure, practical implementation for conversion from raw data, and critical considerations like handling undirected graph symmetry and uniqueness. Understanding the edge list representation. An edge list is perhaps the simplest way to represent a graph. It is a collection of pairs, where each pair code snippet denotes an edge connecting node code snippet to node code snippet. For an undirected graph, an edge code snippet implies a connection between code snippet and code snippet that is bidirectional, meaning code snippet is also connected to code snippet. Structure. Typically, an edge list is stored as a list of tuples or a simple text file where each line contains two node identifiers, like code snippet. Example. Consider a small social network where Alice is friends with Bob and Carol, and Bob is also friend with David. An edge list for this undirected graph would look like: code is not spoken. To get code, please see the link in description or bio. Notice that code snippet is not explicitly listed if the graph is undirected, as code snippet already implies the symmetric connection. When to use an edge list. Simplicity. It's straightforward. RD to understand and implement. Storage efficiency for sparse graphs. For graphs with relatively few edges compared to the number of possible connections, sparse graphs, an edge list can be more memory efficient than an adjacency matrix. Easy parsing. Simple text files are easy to parse into various graph processing libraries. Input data format. The relationship dictionary. Before we can create an edge list, our raw data needs to be in a suitable format. For this example, we assume our raw data has been pre-processed into a Python dictionary, where keys represent source nodes and their values are lists of destination nodes they are connected to. This structure directly reflects one-to-many or many-to-many relationships in the raw data. Expected code snippet format. The input code snippet is structured as a dictionary where keys are unique identifiers for source nodes, e.g., candidate hashes in a referral network. Values are lists of unique identifiers for destination nodes that the source node is connected to. Concrete example. Code is not spoken. To get code, please see the link in description or bio. In this code snippet is connected to code snippet and code snippet. Code snippet is connected to code snippet and code snippet. Even if the raw data only explicitly states code snippet, for an undirected graph, we infer code snippet. Our edge list creation function must handle this symmetry and ensure that each unique, undirected edge is reco. Write only once. Implementing the edge list creation function. The core of this transformation is a Python function that iterates through the code snippet, identifies unique edges, and writes them to a specified output file. A critical aspect is handling the undirected nature of the graph, meaning an edge between code snippet and code snippet is the same as an edge between code snippet and code snippet. Function definition and initialization. Our function, code snippet, takes the code snippet and encode snippet as arguments. It initializes two lists, code snippet to keep track of unique edges already written, and code snippet to collect all distinct node identifiers encountered. Code is not spoken. To get code, please see the link in description or bio. This initial part sets up the function signature, provides type hints for clarity, and defines the purpose of the function, its arguments, and what it returns. The code snippet list will store code snippet objects. Using code snippet is crucial here because code snippet objects are unordered and hashable, making them suitable for checking if an edge, e.g., code snippet, has already been seen, regardless of the order, code snippet, file handling, and node collection. Next, we open the specified output file for writing. We then iterate through each code snippet key in the input code snippet. For each code snippet, we add it to our code snippet list if it hasn't been added already. This ensures we capture all nodes present. In relationships, code is not spoken. To get code, please see the link in description or bio. The code snippet statement is a best practice for file handling in Python, guaranteeing that the file resource is properly managed and closed, processing connections, and ensuring uniqueness/symmetry. This is the core logic where individual edges are identified, deduplicated, and written. For each code snippet, we iterate through its code snippet, which are code snippets. Both code snippet and code snippet are added to code snippet. The critical step involves creating a code snippet using code snippet. Code is not spoken. To get code, please see the link in description or bio. The use of code snippet here is a powerful technique. A code snippet, and thus code snippet, is an unordered collection of unique elements. This means code snippet is considered the same as code snippet. By converting each code snippet pair into a code snippet, we automatically normalize the edge representation. When we check code snippet, we are effectively asking, have we already processed an edge between these two specific nodes, regardless of which one was listed first? This ensures that for an undirected graph, an edge like code snippet is only written once, even if both code snippet and code snippet appear in the raw code snippet. Finalization and return. Finally, after processing all connections, the function prints a summary and returns the code snippet and code snippet lists. Code is not spoken. To get code, please see the link in description or bio. The power of code snippet for undirected edges. As highlighted, the code snippet data structure is central to handling undirected graph symmetry and uniqueness. Why code snippet? 1. Unordered nature. Code snippet is identical to code snippet. This property directly maps to the concept of an undirected edge, where the order of nodes does not matter. If we used a code snippet, e.g., code snippet, it will be distinct from code snippet, leading to duplicate edges in our list. 2. Hashability. Unlike regular code snippet objects are immutable and therefore hashable. This means they can be stored within other sets or used as keys in dictionaries, and crucially, they can be efficiently checked for membership within a list or another set using the code snippet operator. Performance considerations. The current implementation uses a code snippet, to store code snippet objects and checks for membership using code snippet. For very large graphs, checking membership in a list can become slow, in time complexity on average, where n is the number of elements in the list. A more performant approach for very large graphs, if memory allows, will be to store the code snippet objects directly in a code snippet, i.e., code snippet. This would provide average 1 time complexity for membership checks, significantly speeding up the deduplication process. Code is not spoken. To get code, please see the link in description or bio. While this alternative offers better asymptotic performance for lookups, the original approach, list of frozen sets, is often sufficient and simpler to reason about for moderately sized graphs, especially if the primary goal is just to collect unique edges sequentially. Using the code snippet function, a runnable example. Let's put the function into practice with our code snippet and observe the output. Code is not spoken. To get code, please see the link in description or bio. Expected output of code snippet. Code is not spoken. To get code, please see the link in description or bio. Notice that code snippet is not present in the output file, nor in the code snippet list returned by the function. This highlights a key limitation of edge lists, as discussed below. Limitations of edge list representation. While simple and efficient for sparse graphs, edge lists have a notable limitation. Isolated nodes are not captured. An edge list, by definition, only stores information about connections. If a node has no connections, i.e., it's an isolated node, it will not appear in the edge list. In our example, code snippet was present in code snippet but had no connections. Consequently, it does not appear in code snippet or in the code snippet list derived from the edge list creation process. Implications for GNNs and analysis. If your GNN model or graph analysis requires information about all nodes, including isolated ones, an edge list alone is insufficient. You would need a separate list of all node identifiers and potentially their features to ensure all nodes are represented in your graph data object, e.g., code snippet. Node features are typically stored in a separate tensor aligned by node index, where each row corresponds to a node. If an isolated node is missing from your edge list, its corresponding row in the feature matrix might also be missed, leading to an incomplete graph representation. Comparison: edge list versus adjacency list. The choice between an edge list and an adjacency list often depends on the specific task and the characteristics of the graph. Feature edge list, adjacency list. Structure list of pairs code snippet dictionary /list, where each key /index code snippet maps to a list of its neighbor's code snippet. Isolated nodes does not capture isolated nodes, nodes with no edges. Can capture isolated nodes, node code snippet maps to an empty list code snippet. Memory efficiency excellent for sparse graphs, few edges. Excellent for dense graphs, many edges, or when frequent neighbor lookups are needed. Neighbor lookup requires iterating through edges to find neighbors. Direct and efficient, O-degree or O1, average lookup. Edge existence check requires iterating or using a code snippet of edges, O-n or O1 average. NB fast if neighbors are sorted or using a code snippet for neighbors, O-degree or O1 average. Traversal less intuitive for graph traversal algorithms, e.g., BFS/DFS. More intuitive and efficient for graph traversal. Typical use simple storage, input to graph libraries that can convert. Graph algorithms, GNNs requiring direct neighbor access. In summary, if your application strictly deals with connected components or you handle isolated nodes separately, an edge list is a concise and efficient representation. However, for tasks requiring fast neighbor lookups or explicit representation of all nodes, including isolated ones, an adjacency list is often preferred. Many GNN libraries internally convert edge lists to adjacency matrices or sparse tensors for computation. Integrating with graph libraries. Once you have generated your code snippet file, you can easily load it into popular graph processing libraries like NetworkX for general graph analysis, or prepare it for PyTorch Geometric for GNNs. Loading into NetworkX. NetworkX is a powerful Python library for the creation, manipulation, and study of the structure, dynamics, and functions of complex networks. It can directly read edge list files. Code is not spoken. To get code, please see the link in description or bio. The output confirms that code snippet is not part of the NetworkX graph because it had no edges connecting it to other nodes in the code snippet. Preparing for PyTorch Geometric. PyTorch Geometric, PYG, is a library built upon PyTorch for easily writing and training GNNs. PYG's primary data structure is code snippet, which represents a single graph. It typically expects edges to be provided as a code snippet of shape code snippet, known as code snippet, where the first row contains source node indices and the second row contains destination node indices. Node identifiers usually need to be mapped to contiguous integer indices. Code is not spoken. To get code, please see the link in description or bio. This example illustrates how the simple edge list format generated can be transformed into the specific tensor format required by PyTorch Geometric. It also reinforces that any isolated nodes not present in the edge list will not be part of the code snippet object's code snippet or code snippet count unless explicitly added from a separate source of all node IDs. This section focuses on the crucial step of exploring and visualizing graph data after it has been transformed into structured formats like adjacency lists or edge lists. Exploratory data analysis, EDA, for graphs allows us to validate the integrity of our transformed data, understand its fundamental properties, and gain insights into the underlying network structure before applying advanced graph neural network, GNN, models. Loading graph data and initial inspection. The first step in graph EDA is to load our prepared graph data into a suitable graph library. NetworkX is a powerful and widely used Python library for the creation, manipulation, and study of the structure, dynamics, and functions of complex networks. We will load our adjacency list into a NetworkX graph object. Before loading, ensure you have the necessary libraries installed. Code is not spoken. To get code, please see the link in description or bio. Our social network data, derived from the whole staffing problem, is assumed to be stored in an adjacency list format. For this example, let's assume the adjacency list file, code snippet, contains lines where each line represents a node and its neighbors, separated by spaces. For instance, code is not spoken. To get code, please see the link in description or bio. The first element on each line is the source node, and subsequent elements are its neighbors. Additionally, nodes often have associated attributes, e.g., job role, department skills. We can attach these attributes to nodes in our NetworkX graph. For demonstration, we'll create a sample attribute dictionary. In a real scenario, these would likely be loaded from a separate data source, e.g., a CSV file. Code is not spoken. To get code, please see the link in description or bio. This initial block imports the necessary libraries and sets up a placeholder code snippet. In a practical scenario, code snippet would typically be populated by reading a separate data file, e.g., a CSV or JSON, containing node metadata. This separation of structural data, adjacency list, and attribute data is common in real-world graph datasets. Code is not spoken. To get code, please see the link in description or bio. This part handles the core loading. Code snippet parses the adjacency list file, creating nodes and edges based on the defined connections. A code snippet block is included to gracefully handle cases where the file might not exist, providing a fallback dummy graph for continued demonstration. After loading, code snippet efficiently assigns the predefined attribute from code snippet to the corresponding nodes in the code snippet object. It's important to note that code snippet will only apply attributes to nodes already present in the graph. Finally, we print the total number of nodes and edges, which serves as a quick sanity check to ensure the graph loaded as expected. This initial verification step is crucial for debugging and confirming the integrity of your data transformation process. Understanding graph connectivity, connected components. A fundamental property of any graph is its connectivity. A connected component within a graph is a subgraph in which any two nodes are connected to each other by paths, and which is connected to no additional nodes in the supergraph. In simpler terms, if you could trace a path from any node to any other node within a group, and that group is isolated from all other nodes, it's a connected component. Understanding connected components is vital for several reasons. Problem scope. Often, GNNs or other graph algorithms work best on a single, large connected component. Disconnected components might represent isolated groups that don't interact, or they could indicate data quality issues, e.g., missing links. Resource allocation. In our whole staffing problem, a large connected component might represent the core network of candidates who frequently interact or are referred by common contacts. Smaller components or singletons, nodes with no connections, i.e., a connected component of size 1, might be candidates who are harder to place or require different outreach strategies. The presence of many singletons could imply that a significant portion of your candidate pool is not integrated into the referral network, requiring direct sourcing efforts rather than leveraging network effects. Algorithm performance. Many graph algorithms assume a connected graph. Processing a graph with many small components can be inefficient or lead to misleading results if not handled properly. Let's calculate the number of connected components in our code snippet. Code is not spoken. To get code, please see the link in description or bio. The code snippet function provides a quick count of how many distinct, isolated subgraphs exist within our main graph. This metric immediately tells us if our network is a single, cohesive entity or fragmented into multiple groups. Following this, code snippet returns a generator of sets, where each set contains the nodes belonging to a specific connected component. Converting this to a list allows us to inspect individual components and their sizes. A high number of connected components, especially if many are very small or singletons, could indicate that our social network data has many isolated individuals or small cliques. For the whole staffing problem, this could mean many candidates are not interconnected, making it harder to leverage network effects for recruitment and potentially requiring more traditional outreach. Extracting the largest connected component, LCC. In many real-world networks, there is one dominant connected component that contains the vast majority of nodes. This is often referred to as the largest connected component, LCC. For GNNs, it's common practice to focus analysis and training on the LCC because 1. Relevance. It represents the most interconnected and often the most active part of the network. In social networks, this is where most interactions and information flow occur. 2. Computational efficiency. Training on a potentially massive, disconnected graph can be computationally expensive and yield less meaningful results due to the isolated components. Algorithms can often be simplified or run more efficiently on a single connected graph. 3. Algorithm assumptions. Many graph algorithms are designed and perform best on connected graphs. Focusing on the LCC ensures these algorithms operate on the most relevant and well-behaved part of your data. Let's extract the LCC from our code snippet. Code is not spoken. To get code, please see the link in description or bio. Here, we first use code snippet to efficiently identify the set of nodes belonging to the largest connected component. The code snippet argument tells code snippet to compare components based on their size, number of nodes. Once we have this set of nodes, we use code snippet to create a new graph object containing only these nodes and all edges between them. The code snippet is crucial to ensure we're working with an independent graph object, preventing accidental modifications to the original code snippet. This extracted LCC will be the primary focus for our subsequent visualization and analysis, as it represents the most significant and interconnected part of our social network. Visualizing the graph, layouts, and drawing. Visualizing a graph provides immediate qualitative insights into its structure that numerical metrics alone cannot capture. NetworkX integrates seamlessly with Matplotlib for drawing graphs. The key challenge in graph visualization is determining the spatial arrangement of nodes, known as the graph layout. Graph layout algorithms. A good layout algorithm aims to minimize edge crossings, making the graph easier to interpret. Place connected nodes close together, visually representing community structures. Distribute nodes evenly in space, preventing overlaps and dense clumps. Highlight structural properties like clusters, central nodes, or bridges. One of the most popular and intuitive layout algorithms is the Fruchterman-Reingold force-directed algorithm, commonly accessed via code snippet. The intuition behind this algorithm is a physical simulation. Nodes repel each other. Like electrically charged particles, nodes push away from each other, ensuring they don't overlap. Edges attract connected nodes. Like springs, edges pull connected nodes closer together, representing their relationships. Over many iterations, the system settles into a state of equilibrium, producing a layout where highly connected nodes tend to cluster and longer edges stretch between less connected parts of the graph. The code snippet parameter in code snippet is crucial for reproducibility. Without a fixed seed, the random initial placement of nodes will lead to a different layout every time you run the code, making comparisons difficult across different runs or analyses. Setting a code SNE. PET ensures that you get the exact same layout each time, which is essential for consistent analysis debugging, and presentation of your visualizations. Code is not spoken. To get code, please see the link in description or bio. Code snippet computes the code snippet coordinates for each node in the graph, storing them in a dictionary where keys are node IDs and values are number py arrays representing coordinates. We pass code snippet to ensure we are laying out only the largest connected component, which is typically more manageable and representative for visualization. The code snippet ensures that if you run this code multiple times, the initial random placement of nodes, which influences the final layout, will be the same, resulting in an identical visual output. Drawing nodes and edges. Once we have a node positions, we can use NetworkX's drawing functions in conjunction with Matplotlib to render the graph. Code is not spoken. To get code, please see the link in description or bio. This code block orchestrates the actual drawing of the graph. We first create a Matplotlib figure and get its current axis, code snippet. Code snippet draws all nodes in code snippet at their computed code snippetitions, allowing customization of size, color, and transparency. Similarly, code snippet renders the connections. Code snippet adds the node names. For very large graphs, drawing all labels can make the plot unreadable, so it's often commented out or used selectively. Finally, we add a descriptive title, remove the distracting axes, and display the plot. The code snippet command is crucial for saving your visualization for reports, presentations, or further analysis without needing to regenerate it interactively. The code snippet, dots per inch, parameter controls the resolution, and code snippet ensures no plot elements are cut off. Analyzing node connectivity, degree distribution. The degree of a node in a graph is the number of edges connected to it. It's a simple yet powerful metric that tells us about a node's local connectivity. For example, a node with a high degree is a hub or influencer in the network, while a node with a low degree is less connected. In the context of whole staffing, a high-degree candidate might be someone with many referrals or who has referred many others, indicating a strong network presence. The degree distribution of a graph describes how often nodes of a certain degree appear. It's a fundamental characteristic that reveals patterns about the network structure. For instance, a normal or bell-shaped distribution might suggest a relatively homogeneous network where most nodes have an average number of connections. A power law distribution, many low-degree nodes, few high-degree hubs, appearing as a long tail on a rank plot, is characteristic of many real-world networks like social networks or the Internet. This indicates a rich gets richer phenomenon where highly connected nodes tend to attract more. Connections. We can visualize the degree distribution using two common plots. 1. Degree rank plot. Plots the degree of each node against its rank when degrees are sorted in descending order. This helps visualize the presence of high-degree hubs and the overall spread of degrees. It highlights the heavy hitters. 2. Degree histogram. Shows the frequency of each degree value. This gives a clearer picture of which degree values are most common and the overall shape of the distribution. Code is not spoken. To get code, please see the link in description or bio. First, code snippet returns a code snippet object, which we convert into a list of degrees and then sort in descending order to prepare for the rank plot. We then create a Matplotlib figure with two subplots using code snippet. The degree rank plot, code snippet, plots the sorted degrees against their rank, position in the sorted list. A steep drop followed by a long tail, often seen in power law distributions, indicates a network with a few very high-degree nodes, hubs, and many low-degree nodes. In the whole staffing problem, these high-degree nodes would be highly connected candidates, potentially superconnectors or recruiters themselves, who know many other candidates. This plot visually emphasizes the disparity in connectivity. The degree histogram, code snippet, provides a frequency distribution. Code snippet returns a list where the index is the degree value and the value at that index is the count of node. ES with that degree. This plot allows us to quickly see which degree values are most common in the network. For instance, if many nodes have a degree of 1 single connections, it suggests many candidates were only referred by one person or only referred one person themselves, highlighting potential isolated segments. This plot emphasizes the prevalence of different connectivity levels. Both plots complement each other, offering different perspectives on the same underlying distribution. The rank plot emphasizes the presence and magnitude of hubs, while the histogram clearly shows the prevalence of different connectivity levels. Beyond degree, centrality measures, and subgraph visualization. While node degree is a basic measure, other centrality measures provide deeper insights into a node's importance within a network. For instance, betweenness centrality quantifies the extent to which a node acts as a bridge or bottleneck in the network. Nodes with high betweenness centrality are crucial for information flow, as many shortest paths between other pairs of nodes pass through them. In our whole staffing problem, a candidate with high betweenness centrality might be a crucial link between different departments or skill sets, facilitating diverse talent flow. Code is not spoken. To get code, please see the link in description or bio. Calculating code snippet provides a numerical value for each node, indicating its importance as a connector. In the whole staffing context, candidates with high betweenness centrality might be invaluable connectors who bridge different departments or skill sets, even if their direct degree isn't the highest. Identifying these bridges is crucial for understanding information flow and potential referral paths. The second part of this code demonstrates how to visualize a subset of the graph. For very large graphs, plotting the entire LCC might still be overwhelming. By filtering nodes based on criteria, e.g., high degree, specific attributes, or high centrality scores, we can create focused visualizations that highlight particular structural patterns or groups of interest. This technique allows for more targeted exploration and can help in identifying specific clusters or key individuals within network. For example, you might visualize only candidates with a specific code snippet attribute to understand their internal network. Visualizing the adjacency matrix. The adjacency matrix is another fundamental representation of a graph. It is a square matrix where rows and columns correspond to nodes, and a cell code snippet contains a 1 if there is an edge between node code snippet and node code snippet, and a 0 otherwise, for unweighted graphs. For weighted graphs, the cell would contain the weight of the edge. The order of nodes in the matrix corresponds to the internal ordering network X uses, which can be seen by code snippet. Visualizing the adjacency matrix as an image provides a dense, grid-based view of the graph's connectivity. Dense clusters appear as blocks of ones or a dark color along the diagonal, indicating groups of nodes that are highly interconnected. These are often signs of communities or tightly knit groups. Sparsity, a matrix mostly filled with zeros or a light background color, indicates a sparse graph with relatively few connections, meaning most nodes are not directly linked. Symmetry. For undirected graphs, the matrix will be symmetric across the main diagonal, from top left to bottom right. Isolated nodes. Rows and columns filled entirely with zeros indicate nodes with no connections to any other nodes in the represented subgraph. Code is not spoken. To get code, please see the link in description or bio. Code snippet converts our code snippet into a number py array, which is ideal for numerical operations and visualization. Code snippet then displays this matrix as an image. The code snippet color map makes connections, ones, appear dark and non-connections, zeros, appear light, providing a clear visual representation of where connections exist. Code snippet ensures sharp, non-blurry pixels. Interpreting this visualization. Each dark pixel represents a connection between the node corresponding to its row index and the node corresponding to its column index. If you see dense blocks of dark pixels, especially near the diagonal, it suggests the presence of tightly knit communities or clusters within network. These could be groups of candidates from the same company or with highly overlapping skill sets. A largely white matrix implies a sparse network, meaning most nodes are not directly connected to each other. For the whole staffing problem, identifying these clusters can inform strategies for team formation or identifying referral chains. A very sparse matrix might indicate a need for more data collection or different networking approaches. While the spring layout provides an intuitive spatial arrangement, the adjacency matrix offers a compact, quantitative overview of the entire connectivity structure, especially useful for identifying patterns in large, complex graphs. By systematically exploring these graph properties and visualizations, you gain a robust understanding of your network data, which is essential for effective GNN model design and interpretation. This exploratory phase helps validate your ETL process, identify key structural characteristics, and inform subsequent steps in your GNN project pipeline, such as feature engineering or model selection. Pre-processing and loading data into PYG. Efficiently preparing graph data is a foundational step in building powerful graph neural networks, GNNs, with PyTorch geometric PYG. PYG provides specialized data structures and utilities designed to handle the unique challenges of graph data, including heterogeneous node and edge attributes, varying graph sizes, and the need for efficient batching during training. This section delves into PYG's core data handling classes, code snippet, code snippet, code snippet, and code snippet, and demonstrates how to transform raw graph data into the formats required for GNN training. The PYG code snippet object, the core building block. At the heart of PyTorch geometric is the code snippet object. This object serves as a single graph sample, encapsulating all the necessary information for a GNN model. It's essentially a dictionary-like container that stores various attributes as PyTorch tensors. Common attributes of a code snippet object include code snippet, node feature matrix with shape code snippet. Each row corresponds to a node, and columns are its features. Code snippet, graph connectivity in COO format with shape code snippet. The first row contains source nodes, and the second row contains destination nodes for each edge. This format is crucial for efficient sparse tensor operations in GNNs. Code snippet, edge feature matrix with shape code snippet. Code snippet, target labels for each node, shape code snippet, or for the entire graph, shape code snippet. Code snippet, node position matrix with shape code snippet. Code snippet, code snippet, code snippet. Boolean masks indicating which nodes belong to the training, validation, or test sets, respectively. These are typically code snippet in shape. PYG's code snippet object is highly flexible, allowing you to include any other attributes relevant to your graph by simply assigning them, e.g., code snippet. Case A, creating a PYG code snippet object from a NetworkX graph. Often, initial graph exploration and manipulation are performed using libraries like NetworkX. PYG provides a convenient utility to convert NetworkX graph objects directly into PYG code snippet objects, streamlining the transition. First, ensure you have the necessary libraries imported. Code is not spoken. To get code, please see the link in description or bio. This initial setup imports code snippet for tensor operations, code snippet for graph creation and manipulation, code snippet for the core PYG graph object, and code snippet for seamless conversion from NetworkX graphs. Let's create a simple NetworkX graph to demonstrate the conversion. Code is not spoken. To get code, please see the link in description or bio. Here, we construct a code snippet and explicitly add code snippet, node features, and code snippet, node labels, as node attributes. When converting to PYG, code snippet automatically attempts to transfer attributes named code snippet, etc., into the corresponding PYG code snippet object attributes. Now, perform the conversion. Code is not spoken. To get code, please see the link in description or bio. The code snippet function automatically handles the transformation of nodes and edges into PyTorch tensors and assigns them to the appropriate code snippet object attributes. The code snippet output will show a summary of the code snippet object's attributes, indicating their shapes and data types. You can inspect the attributes of the code snippet object to verify its structure. Code is not spoken. To get code, please see the link in description or bio. This output confirms that code snippet holds the node features, Code snippet represents the graph connectivity in the required code snippet format, and code snippet contains the node labels. PYG also infers useful properties like code snippet and code snippet from the code snippet or code snippet tensors, if they are present. Case B, creating a PYG code snippet object from raw files. While NetworkX conversion is convenient, often your raw data will be in simpler formats like edge lists or CSVs. Manually constructing a code snippet object from these raw files provides a deeper understanding of PYG's requirements and offers maximum flexibility. This is particularly useful when dealing with very large data sets or when features are not easily attachable to NetworkX objects. Let's assume we have an edge list file, code snippet, and separate files or methods to derive node features and labels. Step 1. Prepare dummy raw data files. For demonstration, we'll create simple dummy files. In a real-world scenario, you would read these from disk. Code is not spoken. To get code, please see the link in description or bio. These files simulate typical raw data inputs. Code snippet contains pairs of connected nodes. Code snippet contains node IDs and their associated attributes, e.g., industry and job type. Code snippet holds node IDs and their respective classification labels. Step 2. Read edge list and create node-to-index mapping. PYG's code snippet requires node IDs to be contiguous integers starting from 0. If your raw node IDs are arbitrary strings or large integers, you'll need to map them to a compact integer range. Code is not spoken. To get code, please see the link in description or bio. We first read the raw edges and identify all unique node IDs. Then, we create a dictionary code snippet that maps each original node ID to a new, contiguous integer index starting from 0. Sorting code snippet before creating the mapping ensures that the node indices are consistently assigned every time the code runs. Step 3. Prepare node features, code snippet, and labels, code snippet. Node features, code snippet, and labels, code snippet, must be PyTorch tensors. Code snippet should be a code snippet and code snippet typically a code snippet for classification tasks. The number of rows in code snippet and code snippet must match the total number of nodes in your graph, which is code snippet. Code is not spoken. To get code, please see the link in description or bio. Here we first initialize code snippet and code snippet tensors with zeros, ensuring they have the correct shape, code snippet by code snippet for code snippet for code snippet. Then, we read the actual features and labels from our dummy files, using the code snippet mapping to place them at the correct positions in the tensors. Code snippet is code snippet for numerical features, and code snippet is code snippet for discrete classification labels. This example uses two features, industry and job type, for each node, demonstrating how to handle multidimensional node features. Step 4. Prepare edge index, code snippet, and masks, code snippet, code snippet. The code snippet tensor needs to be in COO format, code snippet, and contain the new contiguous PYG indices. Masks are Boolean tensors indicating which nodes are used for training/testing. Code is not spoken. To get code, please see the link in description or bio. The code snippet is created by mapping the original node IDs in code snippet to their new PYG indices. The code snippet call transposes the tensor and ensures it's stored contiguously in memory, which is often required for PyTorch operations. For masks, we create code snippet and code snippet as code snippet tensors. These are Boolean arrays of length code snippet, where code snippet indicates that the cores. Pawning node is part of that split. While older PyTorch versions might use code snippet for Boolean masks, where code snippet means code snippet and code snippet means code snippet. Code snippet is the modern and preferred data type, offering clearer semantic meaning and better performance. If you encounter code snippet masks, convert them to code snippet using the code snippet method. Step 5. Assemble the PYG code snippet object. Finally, combine all the prepared tensors into a code snippet object. Code is not spoken. To get code, please see the link in description or bio. This single line creates the code snippet object, assigning our prepared tensors to its attributes. The resulting code snippet object is now ready to be used by GNN models in PyG. The code snippet and code snippet properties are automatically inferred from the provided code snippet and code snippet attributes, respectively. The PyG code snippet abstraction, code snippet versus code snippet. For real-world GNN applications, you'll often deal with multiple graphs, e.g., a collection of molecules, social networks over time, or graphs too large to fit entirely into memory. PyG provides code snippet and code snippet to manage these scenarios, encapsulating data loading and pre-processing logic for reproducibility and scalability. Feature code snippet. Primary use case: large datasets that don't fit into RAM. Data loaded on the fly: smaller datasets that fit entirely in RAM. Processed once, loaded quickly. Loading strategy: code snippet method loads one graph at a time from disk/source code. Snippet method loads all graphs, processes them, and stores in memory. File storage: raw data, typically stored on disk. Processed data can be cache processed data stored in code snippet and code snippet in memory, and saved to disk for faster future loading. Methods to implement code snippet: code snippet, code snippet, code snippet, optional, code snippet, optional, code snippet, code snippet, code snippet, code snippet, code snippet, code snippet, code snippet. Performance: slower loading per sample, less memory intensive, faster loading after initial processing, more memory intensive. Reproducibility: good, as code snippet can be called to regenerate data. Excellent, as processed data is cached on disk. Both code snippet and code snippet inherit from code snippet, making them compatible with code snippet for batching. The key difference lies in when the data is processed and where it's stored. Code snippet is suitable for truly massive datasets where individual graph samples are loaded and processed on demand, e.g., in the code snippet method. Code snippet is for datasets that, once processed, can fit into RAM. It processes all data once and stores it in memory, making subs. Quick access: very fast. It also handles saving the processed data to disk to avoid reprocessing on subsequent runs. This is often the preferred choice for moderately sized datasets. Both require a code snippet directory argument in their constructor. This code snippet directory typically contains two subdirectories: code snippet for raw, unprocessed data, and code snippet for the processed PyG code snippet objects. The code snippet method, if implemented, fetches raw data into the code snippet directory, and the code snippet method reads from code snippet, performs transformations, and saves the process code snippet objects into the code snippet directory. The code snippet and code snippet arguments allow for data augmentation or feature transformations. Code snippet is applied before the data is saved to the code snippet directory, while code snippet is applied every time a sample is accessed via code snippet. This distinction is useful for computationally expensive transformations that should only be done once, code snippet, versus light transformations or augmentations that should be applied on the fly, code snippet. Case C, creating a PyG code snippet object using a custom class. Let's implement a custom code snippet to encapsulate the manual code snippet object creation logic we just covered. This makes our data pipeline reusable and robust. Code is not spoken. To get code, please see the link in description or bio. The code snippet class inherits from code sni. Pet code snippet initializes the dataset and attempts to load processed data. If not found, it implicitly calls code snippet and code snippet. Code snippet and code snippet, properties that inform PyG about the expected names of raw input files and generated process files. Code snippet. This method is called if code snippet are not found in the code snippet. In a real application, this would fetch data from a remote source. Here, it simulates by copying our dummy files. Code snippet, the core of the dataset. This method is called if code snippet are not found in the code snippet. It contains all the logic to read raw data, perform transformations like node mapping, feature extraction, and construct PyG code snippet objects. Finally, It saves the process code snippet objects using code snippet. The code snippet method. Code snippet is implicitly used by code snippet when saving. For a single code snippet object, it prepares the data and code snippet dictionary needed by PYG to handle multiple graphs efficiently, even if there's only one. The code snippet dictionary stores information about how to slice the combined tensors, code snippet, back into individual code snippet objects when multiple graphs are batched. For a single graph, code snippet will simply indicate the full extent of the tensors. Code snippet returns the total number of graphs in the dataset. Code snippet returns the code snippet object at the specified index. For a single graph code snippet, it simply returns the stored code snippet. Now, let's use our custom dataset. Code is not spoken. To get code, please see the link in description or bio. When code snippet is called for the first time, it checks code snippet. If not found, it calls code snippet and then code snippet, saving the results. On subsequent runs, it will load code snippet directly, providing very fast access. This mechanism ensures reproducibility and efficiency. Batching with code snippet. For training GNNs, especially with multiple graphs, it's essential to process data in many batches. PYG extends PyTorch's code snippet to handle lists of code snippet objects. It intelligently batches multiple graphs into a single large code snippet object, where node and edge indices are offset to distinguish between graphs in the batch. Case D. Creating PYG code snippet objects for use in code snippet. You can directly pass a list of code snippet objects to code snippet. This is useful for simple scenarios or when you generate graphs on the fly without needing a full code snippet class. Code is not spoken. To get code, please see the link in description or bio. We create a second code snippet object, code snippet, to simulate having multiple graphs. Then, we create a list of these code snippet objects and pass it to code snippet. Now, let's iterate through the code snippet to see how it batches the graphs. Code is not spoken. To get code, please see the link in description or bio. When code snippet batches multiple code snippet objects, it combines their attributes into single, larger tensors. For instance, code snippet will contain the node features of all graphs concatenated. To keep track of which nodes belong to which original graph, code snippet adds a code snippet attribute to the combined code snippet object. This code snippet tensor is a code snippet of shape code snippet, where code snippet indicates which original graph the code snippet th node in the combined code snippet tensor belongs to. This mechanism allows GNNs to operate on the combined graph while still respecting the boundaries of individual graphs for operations like pooling or reading out graph-level predictions. Conclusion to data pre-processing. This section has equipped you with the essential knowledge and practical skills to pre-process and load various forms of graph data into PyTorch geometric. From direct NetworkX conversions to manual code snippet object construction with complex features and the robust code snippet for reproducible pipelines, you now understand the core mechanisms. The code snippet then enables efficient batching, a critical step for training GNNs on diverse and often large graph datasets. With this foundation, you are ready to delve into building and training your first graph neural networks. Where to find graph data. Successfully initiating a graph neural network, GNN, project often begins not with model architecture, but with data acquisition. While previous sections focused on transforming existing data into graph formats and preparing it for GNNs, this section shifts our attention to the crucial first step, identifying and acquiring suitable graph data. Understanding where to find relevant data is paramount for any GNN practitioner, as the choice of dataset profoundly impacts the problem definition, model design, and potential applications. Types of graph data sources. Graph data can originate from a variety of sources, each with its own characteristics, advantages, and challenges. We can broadly categorize these sources into publicly available datasets, semantic data models, knowledge graphs, enterprise/private data, and synthetically generated data. Publicly available graph datasets. Public datasets are an excellent starting point for learning, benchmarking, and developing GNNs due to their accessibility and often well-documented nature. Academic benchmark datasets. These datasets are specifically curated by researchers for standardized evaluation of GNN models. They are characterized by their clear problem definitions, e.g., node classification, link prediction, established splits, training, validation, test, and often come with pre-extracted features. Their primary purpose is to enable fair comparisons between different GNN architectures and algorithms. MS. Characteristics, reproducibility, standardized evaluation, often smaller to medium-scale, well-defined tasks. Common examples. Open Graph Benchmark, OGB, a collection of diverse and large-scale graph datasets covering various tasks. Node, link, graph property prediction, from different domains, molecular, academic, social. OGB datasets are designed to push the boundaries of GNN research. Quora, CiteSeer, PubMed, classic citation network datasets widely used for node classification tasks. Nodes represent papers, edges represent citations, and node features are bag-of-words representations of paper content. MUTAG, proteins, molecular datasets used for graph classification tasks, where each graph represents a molecule or protein. Accessing OGB datasets with PyTorch Geometric. PyTorch Geometric, PYG, provides convenient wrappers to download and load many popular benchmark datasets, including those from OGB. This simplifies data acquisition to just a few lines of code. Code is not spoken. To get code, please see the link in description or bio. This code snippet demonstrates how to load the code snippet dataset, a large citation network, directly using PYG's code snippet class. PYG handles the downloading, extraction, and formatting of the graph into its code snippet object structure, making it immediately ready for GNN model training. The code snippet argument specifies where the dataset files should be stored. General-purpose public datasets. Beyond academic benchmark. RKS. Many platforms host a vast array of datasets that can be adapted for graph analysis. These datasets might not be in a direct graph format, e.g., CSV, JSON, but they often contain relational information that can be transformed into graphs, as discussed in creating an edge list. Characteristics, diverse domains, varying quality, often requires significant pre-processing to extract graph structure, larger scale possible. Common examples. Kaggle, a popular platform for data science competitions, hosting numerous datasets across various domains. Many contain relational data that can be converted to graphs, e.g., user item interactions, social networks, transactional data. UCI Machine Learning Repository, a long-standing repository of datasets for machine learning research. While many are tabular, some can be interpreted as graphs, e.g., protein structures, social networks. SNAP, Stanford Network Analysis Project, datasets, a collection of large-scale network datasets from various real-world domains, social networks, communication networks, citation networks, web graphs. These are often provided in simple edge list formats. Downloading and inspecting a general-purpose dataset. For datasets not directly supported by PYG, you might need to download them programmatically using standard Python libraries and then process them. Let's consider a hypothetical simple edge list file. Code is not spoken. To get code, please see the link in description or bio. This example SI, Mulat's downloading a CSV edge list using code snippet for simplicity, but code snippet would be used for a real URL. It then uses code snippet to load the data and code snippet to construct a graph. The code snippet call is crucial for inferring the schema when one isn't explicitly provided. It shows the columns and their inferred data types, which is a fundamental step in understanding the structure of your raw data. Specialized domain-specific repositories. Many scientific and industry domains maintain specialized repositories for their specific data types, some of which are inherently graph-structured or can be easily converted. Examples: bioinformatics, string, protein-protein interaction networks, gene ontology, gene product annotation networks, PubChem, chemical compound networks. Social sciences, ICPSR, Inter-University Consortium for Political and Social Research, for social network data. Semantic data models and knowledge graphs. Unlike raw graph datasets that primarily provide nodes and edges, semantic data models and knowledge graphs offer an explicit schema, rich semantic relationships, and often leverage ontologies. They represent structured knowledge about entities and their relationships, typically using technologies like RDF, Resource Description Framework, and SPERQL. Key difference from graph datasets. Semantic models emphasize the meaning of nodes and edges through explicit type definitions, e.g., person, organization, has author, lives in, and often include reasoning capabilities based on ontological rules. A graph dataset might just have nodes and edges, while a semantic model defines what those nodes and edges represent in a formal, machine-readable way. Use cases in GNNs. Semantic models can be used to enrich existing graph data with external knowledge, provide a structured basis for heterogeneous GNNs, or directly serve as the graph input, where entities and relations are well defined. Common examples. Schema.org, a collaborative effort to create schemas for structured data on the Internet. It provides a vocabulary for describing web content, e.g., product, event, organization. While not a knowledge graph itself, it provides the schema for creating one. Wikidata, a free, collaborative, multilingual knowledge base that acts as a central storage for the structured data of its Wikimedia sister projects. It's a massive knowledge graph that can be queried programmatically. Depedia extracts structured content from Wikipedia and makes it available in RDF format, forming a cross-domain knowledge graph. Industry-specific ontologies. Many industries, e.g., finance, healthcare, manufacturing, develop their own ontologies to standardize data representation and facilitate integration. Examples include FOAF, friend of a friend, for social networks, or SNOMED-CT for clinical terms. Accessing semantic data, conceptual. Accessing data from knowledge graphs often involves using SPERQL, a query law. Language for RDF graphs. While a full SPERQL example is beyond the scope of a beginner PYG book, understanding that these resources are typically queried rather than downloaded as a single file is important. Code is not spoken. To get code, please see the link in description or bio. This conceptual example shows how one might query Wikidata for entities that are humans and have software engineer as an occupation. The key takeaway is that knowledge graphs are dynamic and are typically accessed via query endpoints, allowing you to retrieve specific subsets of the data based on semantic relationships, rather than downloading the entire graph. Enterprise and private data. For many real-world GNN applications in industry, the most valuable data resides within an organization's internal systems. This includes customer relationship management, CRM, databases, transaction logs, sensor data, internal communication systems, and much more. Characteristics: proprietary, large-scale, often unstructured or semi-structured, may lack explicit graph schema. Privacy and security concerns are paramount. Challenges: data silos. Data might be spread across disparate systems. ETL required. Significant effort is often needed to extract, transform, and load EDL. This relational or unstructured data into a graph format suitable for GNNs. This is where the techniques from creating an edge list become indispensable. Data governance. Strict policies around access, usage, and privacy, e.g., GDPR, HIPAA. Lack of explicit schema. Databases might be optimized for transactional operations, not graph relationships, requiring careful schema inference and modeling. Synthetic graph data generation. In certain scenarios, particularly when real-world data is unavailable, sensitive, or lacks specific properties, generating synthetic graph data can be a valuable approach. This is common for testing new algorithms, exploring theoretical properties, or creating controlled environments for experiments. Characteristics: full control over graph properties, size, density, degree distribution, community structure, No privacy concerns, useful for debugging and concept validation. Common models. Erdosrany, GNP, generates a random graph where each pair of dollar and dollar nodes has an edge with probability $p$. Simple, but often doesn't resemble real-world networks. Verabe-Albert, preferential attachment, generates scale-free networks, where few nodes have a very high degree, mimicking many real-world networks, e.g., social networks, citation networks, that exhibit a rich-get-richer phenomenon. Watt-Strogatz, small world, generates networks that exhibit both high clustering, like regular lattices, and short average path lengths, like random graphs, characteristic of small world phenomena, generating a Verabe-Albert graph with Network X. Network X provides simple functions for generating various types of synthetic graphs. Code is not spoken. To get code, please see the link in description or bio. This code generates a Verabe-Albert graph, a common model for networks with power law degree distributions. Such synthetic graphs are invaluable for testing GNNs under control conditions or for generating training data when real data is scarce. Practical considerations for data sourcing. Beyond simply finding data, several critical factors must be considered to ensure the source data is suitable for your GNN project. Evaluating data suitability for GNNs. Not all graph data is equally useful for a given GNN task. A thorough evaluation process is essential. Graph size and density. Nodes and edges. How many? Very small graphs might not generalize well, while extremely large graphs pose computational challenges. Density. Is the graph sparse, few connections, or dense, many connections? GNNs typically perform better on sparse graphs. Node and edge features. Are rich features available for nodes and/or edges? GNNs leverage these features heavily for learning. If features are absent, can they be engineered or imputed? What are the data types of these features? Numerical, categorical, textual. Explicit versus implicit schema. Explicit. Data comes with clear definitions of node types, edge types, and properties, common in knowledge graphs. This simplifies modeling. Implicit. Data is just an edge list or relational tables. You need to infer the schema, define node/edge types, and potentially create features. This is where inspecting code, e-snippet, and code snippet becomes vital. Target task relevance. Does the dataset naturally support the GNN task you intend to perform, e.g., node classification, link prediction, graph classification? For instance, a dataset for protein structures might be ideal for graph classification, while a social network is suited for node classification or link prediction. Class imbalance. For supervised tasks, if your task is classification, are the classes balanced? Severe imbalance can lead to models that perform poorly on minority classes. Temporal aspects. Is the graph static or dynamic, evolving over time? Dynamic graphs require specialized GNN architectures and data handling. Case study. Selecting a dataset for a hypothetical GNN project. Imagine you want to build a GNN to recommend research papers, link prediction, or classify academic fields. Node classification. 1. Initial thought. I need academic papers. 2. Data sources exploration. Public benchmarks. OGB and ArXiv, Quora, CiteSeer, PubMed. These are excellent, pre-processed, and designed for benchmarking. General purpose. Kaggle, e.g. datasets on scientific publications. Might require more cleaning, but offer more flexibility. Semantic models, Wikidata, Deeppedia, could provide rich metadata about papers, authors, and topics, useful for enriching existing data or building a knowledge graph. 3. Suitability evaluation. Example for OGB and ArXiv versus custom Kaggle data. OGB and ArXiv. Pros. Large scale, 170K nodes, 1.1 M. Edges, pre-split, includes node features, abstract embeddings, clear node classification task, academic field. Ideal for benchmarking and immediate GNN application. Cons, fixed task, features might not be exactly what you need for a novel task. Kaggle dataset, e.g., Papers with code dataset. Pros, potentially more flexible, might include authors, venues full text, allows for custom graph construction, e.g., author paper graph, paper concept graph. Cons, requires significant EDL, extracting relationships, creating features from text, no standardized splits, potential data quality issues. 4. Decision. For a beginner project focused on learning GNNs, OGB and Arxiv is a superior choice due to its ease of use and immediate applicability. For a more advanced research project requiring specific feature engineering or unique graph structure, the Kaggle dataset might be preferred despite the extra effort. Data quality and pre-processing challenges. Real-world data, especially from enterprise systems or scraped from the web, is rarely pristine. Expect to encounter various data quality issues. Common issues: missing values, missing node features, edge attributes, or even missing nodes/edges. Noisy data, inaccurate, inconsistent, or erroneous values, e.g., misspelled names, incorrect timestamps. Inconsistent formats, dates in different formats, text encodings, or numerical values stored as strings. Duplicate entities/edges, the same real-world entity or relationship, represented multiple times. Disconnected components. A graph might consist of multiple isolated subgraphs, which can impact GNN message passing. Sparse features. Many features might have zero or near zero values, making them less informative. Initial steps to address. Schema inference. When a dataset lacks an explicit schema, you must infer it by inspecting the data. This involves understanding what each column represents, its data type, its potential role as a node ID, edge ID, feature, or target label. Code snippet code-snippet.info, code snippet.head, code snippet.describe, code snippet value_counts. For categorical columns helps identify unique categories and their distribution. This process helps you define your graph's nodes, edges, features, and target labels. Cleaning. Handling missing values, imputation, removal, correcting errors, standardizing formats. Normalization/scaling. For numerical features, ensuring values are within a consistent range. Feature engineering. Creating new features from existing data to better represent the underlying information. Data licensing and usage rights. When using publicly available datasets, it is crucial to understand and adhere to their licensing terms. Failure to do so can lead to legal issues. Importance. Ensures legal compliance and ethical data usage. Common licenses. MIT license, Apache license 2.0. Permissive open source licenses often used for code, but sometimes for data. They generally allow FRE, e-use, modification, and distribution with attribution. Creative Commons, CC, licenses, specifically designed for creative works and data. CC BY, attribution requires you to give credit to the creator. CC BY SA, attribution share alike requires attribution and that any derivative works are shared under the same license. CC0, no rights reserved public domain dedication, allowing full freedom of use without attribution. Open Data Commons, ODC, licenses, specifically for databases and data. ODC BY, attribution requires attribution. ODC-ODBL, Open Database License requires attribution and share alike. Proprietary licenses. Many datasets from companies or specific research projects may have highly restrictive licenses, limiting commercial use, redistribution, or acquiring specific agreements. Best practices. Always check, before downloading or using any public dataset, locate its license information. Attribute. If the license requires attribution, clearly credit the data source in your work, e.g., in research papers, project reports, or code comments. Understand restrictions. Be aware of limitations on commercial use, modification, or redistribution. By carefully considering these aspects of data sourcing, you can lay a solid foundation for successful GNN development, ensuring your projects are built on relevant, high-quality, and legally compliant data. Graph data preparation for GNNs. A comprehensive recap. Preparing graph data for graph neural networks, GNNs, is a foundational step, distinct from traditional machine learning data pipelines due to the inherent relational structure of the data. This section consolidates the critical considerations and practical steps involved, from initial data modeling to loading data into GNN-specific libraries, designing robust graph data models and schemas. The first and often most crucial step in any GNN project is designing an effective graph data model and schema. This involves identifying nodes, entities, edges, relationships, and their associated attributes. Importance of iterative design and refinement. Unlike tabular data, where features are often clearly defined, relationships in graph data can be ambiguous or evolve over time. This complexity necessitates an iterative and adaptive approach to schema design. Initial designs are rarely perfect. Expect to refine your schema as you gain deeper insights from your data, encounter new data sources, or clarify project objectives. Skipping this iterative process can lead to significant technical debt, requiring costly refactoring later in the project. The critical role of domain expertise. While technical skills are essential, domain expertise is paramount for effective schema design. A deep understanding of the real-world system you're modeling, e.g., a social network, a molecular structure, a supply chain, allows you to accurately identify relevant entities and their types, define meaningful relationships and their directions, e.g., works_at, knows, purchased, prioritize attributes that are truly predictive or informative for your GNN task. For instance, in a recruitment firm scenario, domain experts can identify that employee and job_opening are nodes and referred or applied_ are edges. They can also specify crucial attributes like skill_set for employees or required_experience for job openings. Without this insight, a schema might miss critical connections or include irrelevant data, hindering GNN performance. Example, basic schema definition. A graph schema can be conceptually defined using Python dictionaries or classes, outlining node and edge types with their expected properties. Code is not spoken. To get code, please see the link in description or bio. This schema provides a blueprint for how your raw data should be transformed into nodes and edges, specifying their types and attributes. This structured approach helps in data validation and consistency. Graph representations and their practical implications. Once a schema is defined, the raw data must be transformed into a suitable graph representation. The most common representations are adjacency lists, edge lists, and adjacency matrices. Each has distinct memory and computational trade-offs. Adjacency list stores a list of neighbors for each node. Memory, efficient for sparse graphs, graphs with relatively few edges compared to the maximum possible. Computation, fast for iterating over neighbors of a specific node. Use case, ideal for most GNNs where neighborhood aggregation is key. Edge list, stores a list of source, target, pairs representing edges. Memory, very compact, especially for sparse graphs. Computation, requires iteration to find neighbors, less efficient than adjacency list for neighborhood lookups. Use case, simple to generate from raw data, often the intermediate format before converting to other representations or GNN-specific formats. Adjacency matrix, and $n times $n matrix, where $and is the number of nodes, where an entry code snippet is 1 if an edge exists between node code snippet and node code snippet, and 0 otherwise. Memory, inefficient for sparse graphs, stores many zeros. Can be very large, $n$2. Computation, efficient for matrix multiplication operations, crucial for some graph algorithms and early GNN formulations. Use case, best for dense graphs or when linear algebra operations are primary. For GNNs, sparse matrix formats are preferred for efficiency. Example, converting between representations. Let's illustrate the conversion between an edge list and an adjacency list using a simple graph. Code is not spoken. To get code, please see the link in description or bio. The edge list is often the most natural way to represent raw relational data. Code is not spoken. To get code, please see the link in description or bio. The JSON. SciList is highly efficient for accessing a node's neighbors, which is a common operation in GNN message passing. Data serialization and encoding. Once data is transformed into a graph representation, it needs to be stored or transmitted. The choice of serialization format depends on factors like readability, portability, memory efficiency, and system compatibility. JSON, JavaScript object notation. Pros: human readable, widely supported, excellent for web APIs. Cons: can be verbose, less memory efficient for very large graphs. Use case: configuration files, small to medium-sized graphs, exchanging data with web services. CSV, comma-separated values. Pros: simple, universal, good for tabular data, node features, edge lists. Cons: no inherent graph structure, requires parsing to reconstruct relations. Use case: storing node/edge attributes in a tabular format, simple edge lists. Pickle, Python-specific serialization. Pros: preserves Python object structure, e.g., NetworkX graph objects, easy to use within Python. Cons: not language agnostic, security risks with untrusted data. Use case: saving and loading intermediate Python graph objects for quick restarts or internal processing. Sparse matrix formats, e.g., COO, CSR. Pros: highly memory efficient for large, sparse graphs, optimized for matrix operations. Cons: not human readable, require specific libraries, e.g., code snippet. Use case: storing the adjacency matrix of very large graphs in memory con. Strain environments or for fast linear algebra. Example: serializing a NetworkX graph to JSON. NetworkX graphs, being Python objects, can be easily serialized. While NetworkX has its own JSON format, a more general approach is to convert it to a simple dictionary structure first. Code is not spoken. To get code, please see the link in description or bio. This sets up a small graph with node attributes. Code is not spoken. To get code, please see the link in description or bio. This JSON format is widely interoperable and readable. Code is not spoken. To get code, please see the link in description or bio. This demonstrates the round trip of serialization and deserialization, crucial for persistent storage or data exchange. Building graph data pipelines, EDL, a robust extract, transform, load, EDL, pipeline is essential for consistently preparing graph data. Extract involves gathering raw data from various sources, databases, APIs, log files. Transform, the most complex stage, where raw data is converted into graph structures, cleaned, and features are engineered. This is where schema design choices are implemented. Load involves storing the processed graph data into a suitable format for GNN training, e.g., PYG code snippet objects, graph databases. Common challenges in graph EDL. Temporal dynamics. Graphs often change over time. New nodes, edges, evolving attributes. The pipeline must handle these updates, potentially requiring snapshotting or streaming AP. Proix. Multi-relational graphs. Data may contain multiple types of relationships, e.g., friend underscore, works underscore at, likes. The EDL process must correctly identify and represent these distinct edge types. Very large data sets. Scaling EDL to billions of nodes and edges requires distributed processing frameworks, e.g., Apache Spark, DasGraph. Dirty and dynamic data. Real-world data is often incomplete, inconsistent, or contains errors. The ETL pipeline must incorporate robust data cleaning, deduplication, and imputation strategies. For instance, in a recruitment firm, new applicants arrive daily, skills change, and some profiles might have missing information. The ETL pipeline needs to manage these continuous updates and data quality issues. Example, a simple data transformation step. Imagine you have employee data in a tabular format, and you want to create collaborates_on edges based on shared projects. Code is not spoken. To get code, please see the link in description or bio. This is a typical tabular input. Code is not spoken. To get code, please see the link in description or bio. This transformation logic generates edges from tabular data, a common ETL step, exploratory data analysis, EDA, and visualization with NetworkX. Before feeding data into a GNN, it's crucial to perform EDA to understand the graph structure, identify potential issues, and gain insights. NetworkX is an invaluable Python library for this purpose. NetworkX allows you to load and manipulate graphs, create graphs from various data sources, add, remove nodes and edges, calculate graph metrics, compute node degrees, centrality measures, connected components, shortest paths, etc. Visualize graphs. Create basic network diagrams to visually inspect the graph structure. Example: basic NetworkX EDA and visualization. Code is not spoken. To get code, please see the link in description or bio. This provides basic structural insights. Code is not spoken. To get code, please see the link in description or bio. Visualizing the graph helps in quickly identifying clusters, central nodes, or disconnected components. For example, in a referral network, you might quickly spot highly connected individuals, influencers, or isolated groups. Pre-processing and loading data into PyTorch Geometric (PyG). PyTorch Geometric (PyG) provides specialized data structures and utilities for efficiently handling graph data for GNN training. The core classes are Code Snippet, and Code Snippet. Code Snippet, a single graph object storing node features, Code Snippet, edge indices, Code Snippet, edge features, Code Snippet, and labels, Code Snippet. It's designed to be flexible and efficient. Code Snippet, a collection of code snippet objects. PyG offers Code Snippet for datasets that fit into memory and Code Snippet for larger, disk-based datasets. Code Snippet iterates over a code snippet, automatically batching code snippet objects into a single code snippet object, which is optimized for GPU processing. Example: creating a PyG code snippet object and code snippet. Let's convert our simple NetworkX graph to a PyG code snippet object and then use a code snippet. Code is not spoken. To get code, please see the link in description or bio. This defines the minimal components for a code snippet object: node features, code snippet, and edge connectivity, code snippet. Code is not spoken. To get code, please see the link in description or bio. The code snippet object encapsulates all information for a single graph. Code is not spoken. To get code, please see the link in description or bio. The code snippet class provides an interface for managing collections of graphs, handling loading and saving. Code is not spoken. To get code, please see the link in description or bio. The code snippet is crucial for efficient training, especially when dealing with many graphs, as it handles batching and memory management. Real-world context and final considerations. Successfully applying GNNs in real-world scenarios, such as the recruitment firm's candidate referral network, hinges on thorough data preparation. This includes handling dirty data. Real-world data is rarely clean. The methods discussed, schema design, ETL, provide a framework for managing missing values, inconsistencies, and evolving data. For example, if a candidate skill list is incomplete, the graph structure might still allow for inferring missing skills from ConnectShow, NS to other candidates or job openings. Scalability. For very large graphs, memory efficiency and distributed processing become critical. Sparse matrix formats and specialized graph processing engines are often necessary. Ethical considerations. Data privacy, e.g., GDPR, CCPA, is paramount, especially in sensitive domains like social networks or recruitment. Data preparation must ensure anonymization, consent, and secure handling of personal information. Explainability. While GNNs can be powerful, their black box nature can be a challenge. Good data modeling and clear feature definitions can aid in interpreting model predictions and building trust. Understanding the utility and limitations of public graph datasets like Cora, CiteSeer, PubMed is also important. While they serve as excellent starting points for learning and benchmarking, their structure and features may not perfectly align with the complexities of real-world proprietary data. Often, real-world applications require a significant investment in custom data engineering to convert raw, messy data into a GNN-ready format.